So everyone able to hear me? Raise the hands. Just 1 second. Let me switch on the light. Right. So audio, video, and everything are clear now. Is confirmed. Good evening. So everything is confirmed, I think. Right. Clear, I think. Yeah. So audio will increase slowly. Don't worry. So when I discuss, the audio will increase. So audio is now high. Right. Done. See, I agree that on day one we have some technical issues. But remaining second day, third day, and fourth day, if I'm correct, we don't have any technical issues. Right? Is it right? Raise the hands. Is it right? Right. See, one or two student has like texted that there are some technical issues. I admit that on day one we have technical issues. I have given the complaint there. The issue was resolved. The technical problem was solved, and everything is fine. So please, when you are texting to that host, please go through. So it is not blindly you text the things that will irritate a teacher. That is not fair. Why? Because when I'm taking all the care, I'm asking every time whether you are able to audible or everything. When I'm asking, you are not supposed to like blindly text a technical issue. You check from your side whether you have a network issue or you don't have any network issue. You cannot directly comment on a teacher. Better you try to mind it. On day one, I agree that we have a technical issue from my side because of this rainy season. It was rectified with like what step I have taken to rectify that. So please remember that. Right. So my video is visible. My video is visible. Some told it is not visible. My video is visible. Right. Now it is visible, right? Done. Fine. Now everything is fine. Now we'll start the class. Now my video is visible, right? Right. So text me at least one. Sir, everything is fine and clear. Text me. Right. All clear, sir. All clear, sir. Fine. Now we start the class. Right. Fine. Now let us not see this box. Fine. One request to all the students. See, if you are having any technical issues, right? Definitely it will be common to all the students. So during that time, please try to raise the hands. Not like literally you raise the hands, just raise the hand. So from that I can understand that there is some technical issue from my side. I'll try to rectify. If 1, 2, 3 are raising, it means it is not from my side, it is from your side. Please try to understand that, right? And one more student has called me, right? So he told me to just speed up, so fast up. Shall I maintain the same speed or shall I increase the speed? Please text me. Shall I maintain the same speed or shall I increase the speed? Little increase little bit. This is good, sir. This is good, sir. Same speed, don't increase. Right. Anyhow, I'll try to moderately increase. Okay, I can understand the issues. Now, don't text anything. I'm back into the subject. Please don't text anything, please. Right, I'm not looking into the box. It is clear. And before I start the class, one final request from my side. If any technical issues from my side, if the video is struck, the audio is struck, anything is struck, please at a bunch you try to raise the hands. It directly says that the issue is from my side. If 2, 3, 4 are raising the hands, it is not from my side, it is from your side. Try to rectify that, right? So I told you that on war step I have taken all the problems to be resolved. I have resolved that, right? Please try to mind that. Right? Anyhow, Oh, this is in the morning I have discussed. Right. So I'll go by this black background. Right. So one small announcement. I'll do it in the middle of the class. Don't worry. Fine. So I'll start the class where I was in my last class. So it is blue. I'll go for completely black. Completely black. Draw white color. Fine. View. Paper style. Marking. Fine. Right. So in my last class, I was discussing about the concept of pole formation for AC machines, right? So if you recall, I told you that we define poles per phase. So I told you what is called as a phase. Phase refers to a winding, and a winding will have series and parallel connection of coils, and a coil will have turns, and the turns will have two conductors. And please remember that these two conductors should be apart by 180 degrees for full pitch for a maximum voltage in that, right? Why? Because when I was discussing about the concept of the turn, I told you that if you want to add up the voltages, you need to connect the conductors which are lying under opposite pole. So what is the electrical angle between those two poles? It is 180 degrees electrical, right? Now let us go for the next concept. So before I start, so can I write phase? So let me just type here day 5. What is the date today? 9, I think. 9/07/2021. Right, done. Right. Poles per phase. What is that? Phase. Phase refers to windings. Refers to windings. Right. And windings have series and parallel connection of coils. Coils. Coil consists of turns. Turn consists of two conductors joined by end connections. End connections. End connections. I hope you understood what is called as a phase, what is called as a winding. See, in most of the interviews, this question is asked to most of the students. Is there any difference between a phase and a winding? No, there is no difference between a phase and winding. I can exchangeably call a phase as a winding or a winding as a phase. Then what a winding will have? A winding will have series and parallel connection of coils. Or why we need to connect the coils in series and parallel? So the series connection is to increase the voltage rating and parallel connection is to increase the current rating. Or why we need to increase the voltage and current rating for increasing the power rating? P is equal to VI, right? Done. Then why we need to have a coil? It is over. Why we need to have a turn? Then I told you that it is not possible to get a voltage of 230 with a single turn. Why? Because the voltage that is induced in each conductor will be less, and if you want to add up, then I need to go for the turns. I hope this is clear. Confirm me all of you. Confirm me all of you. Right. Now I'll be explaining the concept of pole formation. So day before, one student was asking one doubt. Sir, is there any relationship between poles and phases? See, we don't have any relation. We design poles per phase. Remember, we design poles per phase. For example, I'm having R phase. It is designed for 2 poles. I'm having the same R phase. It can be designed for 4 poles. I'm having the same R phase. It can be designed for 100 poles. So we design poles per phase. Please remember that. So in order to explain the concept of pole formation, I consider one phase now. In that phase, there is only one coil now. In that, there is only one turn now. There is only one turn now, right? So I consider here design of two pole machine. So I need to design how many poles per phase? I need to design two poles. So for that, what I'll try to do means I'll consider one coil. I consider one coil. In that coil, I'll consider only one turn. So that coil can have any number of turns, but I'm considering only one turn. So in this one turn, how many conductors will be there? Two conductors will be there. If you remember, two conductors will be there, right? So let us consider what are those two conductors. So this is conductor 1, this is conductor 2. I name it as A, I name it as A dash. And these two are joined with end connections like this. So here, what is that excitation I'm giving to this means I'm designing poles per phase. So I have to give a per phase voltage. So I'm giving a single phase AC here, AC here. So this is a coil with how many turns? There is only one turn. Then how many conductors we are having? Only two conductors, right? So this is only one coil. So how many poles I'm designing? Two poles. Now let me explain the concept of pole formation, how to design. Please see. So here I'll consider a stator like this. In this stator, I'll be considering only two slots. Two slots. This is slot. This is one slot. Right? So this is A. I'm placing this first conductor in this slot. So I'm not drawing internally. This is the second conductor A dash. You know that the angle between the two conductor sides has to be 180 degrees electrical. Why? Because we need to add up the voltages, then those conductors should be under opposite poles, right? Please. So opposite poles means if one is under north pole, the other one has to be under south pole. So those opposite poles may be adjacent side poles also, but they should be under opposite poles. Please remember that. Now see, I'm giving a AC. So I'm calling this one as node A and I'm calling this one as node B. So during the positive half cycle, what happened means, so this will be at high potential compared to this during positive half cycle. If that is the case, this conductor A will carry the current into, and this current flows through the coil, and the same current is supplied to the source by conductor A dash. So who is collecting the current from that source means conductor A is collecting the current, and who is returning the current to the source means the conductor A dash is returning the current to the source. So I assume that the collecting current is into here, and the receiving the supplied back current, I'll take it as a dot, right? Is it clear? Confirm me. Is it clear? Confirm me. So which conductor is collecting the current? A, and which current is supplying the current back? A dash, right? So collected current, received current, I'm putting it as into, and the supplied current back, I'm taking that as a dot. Now you know that every current carrying conductor will produce as a magnetic field. Now I need to find out the direction of magnetic flux lines. So if I want to find out the direction of magnetic flux lines, which rule I need to call upon? Right hand thumb rule. So with respect to this, I'm trying to draw like this. So don't draw any flux lines above the core. No flux lines will travel like this. So if I try to draw the flux lines, it will be like this. It will be like this, like this. Then if you observe carefully here, so from one side of the core, so this side of the core, the magnetic field lines are coming out. It looks like they are coming out. And from other side, the magnetic field lines are entering. So if you just imagine a bar magnet, and with respect to a bar magnet, if you can remember, with respect to a north pole, the magnetic field lines will leave the core. And with respect to the south pole, the magnetic flux lines will enter the core. So if the magnetic field lines are leaving the core, you can see this is the stator core. if the magnetic field lines are leaving the core, or if they are traveling from core into air, if they are traveling from core into air, then what is the pole that can be imagined there? I can imagine a north pole here. And if the same magnetic field lines are entering the core, or if they're traveling from air into core, I can imagine a south pole here. So like this, how many pole pairs are formed inside that? There is only one pole pair is formed. North and south poles are formed. But is this pole polarity fixed or they will change? No, these pole polarities will not fix. Why? Because it is true that during the positive cycle, conductor A will carry the current, but the conductor A dash is returning the current. But when I'm talking about the negative cycle, so which conductor will carrying the current means A dash will carry the current, and which conductor will return the current means A will return the current. If that is the case, you can see there is a north pole here and there is a south pole here. Then finally, what will be the nature of this field means, so the nature of field will be standing and it is pulsating. So the field will be oscillating here. So in one cycle, the field will be from north to south, in the other way left to right, and other way, in other cycle, the field will be from south, from this side to this side. So the field will be oscillating. It will be oscillating like this. So along one axis, it will be oscillating. So it is a stationary and oscillating field. The poles are oscillating like this. The poles are oscillating like this. But how many poles are formed here? Two poles. So can I say like this, with only one coil, so how many poles I can form? Two poles. So can I say this particular phase A, if I'm calling this one as phase A, this is a phase A. This particular pole phase A is designed for how many poles? It is for two poles. So it is two poles. So when that for when particularly for that phase A, if you are giving a single phase supply, so what will be the nature of those poles? Means they are stationary and pulsating. That means oscillating. As the poles are stationary and oscillating, the field produced by such stationary and oscillating poles is also stationary and oscillating. So in one cycle, the field lines will be like this. In other cycle, the field lines will be like this. So the field lines will be oscillating along the same axis. Like this, they will be oscillating. Is this point clear? Is this point clear, all of you? Right. So can I say the nature of poles formed with the single phase windings and the single phase AC excitation, the nature of poles formed with the single phase winding and single phase AC excitation are stationary and oscillating. Stationary and oscillating. As the poles are stationary and oscillating, the field, the flux produced by such stationary and oscillating poles is also stationary and oscillating. So you can see there is only one alternating field along that axis, right? I'll give the same statement. The nature of, so one thing, you want me to write everything on the board or just it is enough to dictate? You want me to write? Raise the hand if you want me to write. Right, please, I'm writing. The nature of poles formed with single phase windings and single phase excitation are stationary and pulsating, or standing and pulsating. Pulsating, right? It is clear. So if anyone questions you, Array, you have taken one stator. In the stator, you have placed one coil with only one turn. Then can you please tell me for how many poles that phase A is designed for? I can say that phase A is designed for two poles. So if anyone questions you, do we have any relation with number of phases and number of poles? We don't have any relation at all. We design poles per phase. Now it is two poles per phase, right? I think it is clear. Now we are talking about a three-phase induction motor. So when we are talking about a three-phase induction motor, so in this particular phase, just one second, just 1 second. I'll come back. 1 second. Right. So the nature of poles formed with a single phase winding and single phase AC excitation is stationary and alternating. For say, if you are giving a DC, for say if you are giving a DC, if you are giving a DC, then you can see this A will be always positive. When A is always positive, that conductor A will always carry the current, and B will be negative. If that is the case, that conductor A dash will return the current. If that is the case, so this pole will be always north this side, and this way pole will be always south, and the direction of field will be always unidirectional. It will be from north to south. With respect to this case, it will be traveling from left to right. So there is no oscillation of the field. It is only a unidirectional. It is one directional field from north to south we can expect. I hope this point is clear. Confirm me once. Right. But here, we are talking about a three-phase induction motor. So when we are talking about a three-phase induction motor, so how many phases I need to place here? I need to place three phases. So when I'm talking about the concept of rotating magnetic field, I made a point very clear on that day. Whenever we talk about three-phase windings, please remember that the number of turns per phase should remain same. The poles per phase should remain same. The space angle between them should be 120 degrees electrical. So if you just recall this, for how many poles that particular phase A is designed, it is for two poles it is designed. As it is designed for two poles, how many coils are required? There is only one coil is required. So if I want to design the poles for second phase also, for phase B also, I need a single coil. So number of turns should be same. That means in the first case, how many turns we have taken? 1 turn. So even for the second phase also, as we need to design two poles, I need only one coil, and even in that I need 1 turn. So phase B, if I'm going to represent how many conductors are required even for phase B, I need 2 conductors. Similarly, how many conductors are required for phase C? I need 2 conductors. So these are three phases, right? So each phase is designed for how many poles? 2 poles. Now the question comes, how to place these conductors in the stator slots, right? How to place these conductors in the stator slots? Now if you recall, I told you that the physical spacing between the windings has to be 120 degrees electrical. I mean to say that if I'm placing one conductor of phase A, in one slot, then with respect to that, the other conductor has to be placed at an angle of 120 degrees. That means phase B conductor has to place at an angle of 120 degrees. And from that, the phase C conductor has to place at an angle of 120 degrees. So can I say like this? As we are designing a three-phase winding, so by properties of a three-phase windings, it is clear that the number of turns per phase should remain same. So here phase A, I took it for 1 turn. Even for phase B also I need to take 1 turn, and even for phase C also I need to take 1 turn. So 1 turn means how many conductors will be there? For phase B, there will be 2 conductors, and for phase C, there will be 2 conductors. Like that, how many conductors will be there? All together, 6 conductors will be there. Why? Because two conductors per phase. Then how to place these conductors means, so the angle between first conductor of phase A and the first conductor of phase B should be 120 degrees electrical. Similarly, the angle between the first conductor of phase C and phase B should be 120 degrees. So between A and B, what has to be the angle? 120 degrees. Between B and C, what has to be the angle? 120 degrees. Similarly, what has to be the angle between A and A dash? 180. B and B dash 180, C and C dash 180. Why? Because A dash represents single phase. So the angle between them should be 180. AB, different phases, should be 120. I hope this point is clear. Confirm me all of you. Confirm me all of you. Right. So I'm trying to draw a stator with how many phases here? 3 phases, right? So first let me draw that. Then after that, we'll try to give a 3-phase excitation. See, please hold me. So I'm trying to draw a stator with how many phases here? 3 phases. 3 phases. So let me just draw. This is for phase A. A A dash. It is phase A. What has to be the angle between A and A dash? 180 degrees electrical. So with respect to A, the B phase has to be after how many degrees? 120 degrees. So it is B. It is a B dash. Similarly, this is C. This is C dash. C dash, right? So can I say this is a stator with how many phases? Three phases. And in each phase, how many coils? One coil. And in each coil, how many turns? One turn. And in each turn, how many conductors? Two turn conductors. What are those two conductors? A and A dash, B and B dash, C and C dash. What has to be the angle between A and A dash? 180. What has to be the angle between A and B? 120. I hope this is clear. Please confirm. Right. So internally, A dash, B dash, C dash are joined. Internally, A dash, B dash, C dash are joined. It indicates that the windings are connected in star. Then from that, I'm taking out the three phases. What are those three phases? A, B, C. I'm taking out the three phases. Then what is that excitation I need to give to that A, B, C? I have to give a three-phase supply. And again, you know what is the basic fundamental properties of a three-phase supply? The three-phase supply means those currents should be either sine or cosine sinusoidally varying. The frequency should be same, the peak value should be same, and the time angle should be 120 degrees electrical. This means with respect to peaks, there should be a shift of 120 degrees in time, right? So let me draw those three-phase currents. I'm drawing a three-phase currents. I'm once again reminding you, if any technical issue from my side, if anything is struck, at a glance, all of you raise the hands. Please remember that. If 1, 2, 3 are raising means I'm not going to stop. Why? Because the problem may be from your side. Please remember that. Even I spoke to some students, right? After that text, sorry, is there any technical issue in the second, third and fourth day? He said, no, sir, it is correct. Only first day we have. Please, Baba, please try to help me. So I'm trying to draw a three-phase supply. So three-phase means red. I'm trying to draw roughly like this. This is R phase. Then Y. Y will be after how many degrees, Baba? 120 degrees. This is Y. Then after that, we'll be having blue, B phase. So these are the three phase currents, right? You can see the magnitudes are same, the frequencies are same, and the time angle between those currents is something like 120 degrees electrical. I name it as IA, I name it as IB, I name it as IC, right? Now the question is, you can see here, each phase is designed for two poles. Each phase is designed for two poles. When you are giving a single phase AC to any of the phases, if you give to A phase or B phase or C phase, then individually I'm talking, then what will be the nature of those poles? Those poles are stationary and alternating. Now, instead of giving a single phase excitation to a single phase, either A, B, C, now if I try to give a three-phase excitation to all three phases at a time, then what will be the nature of those two poles? So still they will be oscillating or the poles will be rotating. We'll try to check, right? Now we are trying to see what will be the nature of those two poles if I'm giving a three-phase supply. Then what will be the nature of those two poles if I'm giving a single-phase supply? Those poles are stationary and oscillating. Now if I give a three-phase supply, what will be the nature of those poles? We are going to check now. Is it clear? Is it clear? Right. Now, I'm trying to explain with respect to four instants of time. Four instants of time. What are those four instants of time is? See, I'll consider this is one instant. This is one instant. I'll consider this is one more instant. I consider one more instant, and I consider one more instant. So this is omega t, right? I name this time as T1, T2, T3. And sorry, this is not this instant. I'm taking this instant, T4. And you can see T4. You can see it is every 60 degrees. So I need to indicate what will be the nature of those two poles when you are giving a three-phase excitation. So for how many instants of time I need to draw the stator now? I need to draw for 4 instants of time, right? Please see. Please see, all of you. This is one. Let me copy this. Right? Unnecessarily wasting time. Something like this. Just hold for some time. Right. One more instant. Right. So 4 instants of time. Now let us go for placing of those conductors. As usual, you know that. So the angle between the conductors of the same phase is 180. The angle between the conductors between two phases should be 120. So let me just do it. So this is for A dash, A dash. After 120 degrees, this is for B dash. This is for C dash. Like this, A dash, B dash, C dash. Similarly, A dash, B dash, C dash. Similarly, last one, A dash, B dash, C dash, right? So let me construct the stator. Right. So it will take some time, try to understand. So can I say these are for 4 instants of time, right? Let me go for instant of time T1. Now, before to that, you please answer me with respect to this example. if any conductor is carrying current, then what is the notation we have taken? Cross. And if any conductor is returning the current, we have taken it as dot. Is it clear? Right? Right. Done. So please, all of you raise the hands. Only if you are raising. Please, I need answers from all. Right. Done. So can I say like this? Can I say like this? During positive cycle, that conductor A is carrying the current, and during negative cycle, the conductor A dash is carrying the current. Why? Because during positive cycle, when conductor A is carrying the current, A dash is returning. During negative cycle, A dash is taking the current and A is returning the current, right? It is what we have seen. Now let us see. So this is omega t. So above to this is positive values and below to this are negative values, right? Then I'll take 4 instants of time. What are those 4? So first I consider the instant of time t1. So if you look into this time instant time t1, so at instant time t1, we can see the magnitude of current Ia is positive. That means current value Ia is positive. At the same time, the current B and C are negative. Of course, it is Im and Im by 2, Im by 2. I'm not taking that. I'm talking whether positive or negative. So you can see Ia is positive and Ib and Ic are negative. So at time t1, which we have considered, which current is positive Ia, which current is negative Ib, and also Ic. Is this point clear? Confirm? All right. So if that is the case, as phase A is positive, then conductor A will carry the current. I'll just zoom this. I can zoom this. So conductor A will carry the current. A dash will return the current. Why? Because A is positive. What happened to B and C? Negative. When B and C are negative, then which one will carry the current? B dash will carry the current. And which will return the current? B will return the current. Similarly, C is negative, means which one will carry the current? C dash, and which will return the current? C. Is this point clear? Is this point clear? Once again, I'm repeating. If we just see this at the instant of time t1, which one is positive? So here, Ia is positive. Which one is negative? Ib and Ic are negative, right? So when Ia is positive, then I can say conductor A will carry the current, A dash will return the current. If Ib is negative, means B dash will carry the current, B will return the current. Similarly, C dash will carry the current and C will return the current. So here, so during this time, you can see this is positive, this is negative, right? So here A is carrying the current, here B dash is carrying the current, here C dash is carrying the current, right? So they are carrying the currents cross and the remaining things are dot. So this is what I have shown here. Then I want to find out the resultant flux. So if I want to find out the resultant flux, so I'll be looping all. I think in my last class, I told you that if the two consecutive conductors are carrying the currents in the same direction, if the magnitudes of those currents are same, then there will not be any flux lines between those two conductors. Yesterday we have seen that, right? I'm not repeating that. You can see this conductor and this conductors are carrying the current in same direction, and there will not be any flux lines passing through between those conductors. The resultant will be like this, like this, like this. Similarly, the bottom section, if I'm trying to apply the left hand right hand thumb rule, like this. So the currents are like this. The flux lines will be like this. So the currents are upwards, the flux lines will be like this. So this is the air. Then you can see with respect to this air, the magnetic field lines are coming from core into air like this, from air into core like this. So when the magnetic flux lines are traveling from core into air, then what is the pole that can be imagined here? North pole. And what will be the pole that can be imagined here? A south pole. Like that, the same pole pair is formed at the instant of time t1, right? Now let us see with the time, with the changes in current magnitudes Ia, Ib, Ic, whether these poles are oscillating or these poles are rotating. We are trying to see now, right? So this is at the instant of time t1. It is something like your car is stationary. The car is standing now. You are having a four-wheeler, it is standing now. So the poles are as of now standing. But you know that with the time, with the time, with the time, so the magnitudes will be changing now. Now, when I'm talking about T2, what will be the magnitudes of IA and IB? You can see they are above the positive, I mean, omega T. So they are positive. So at T2, A is positive, B is also positive, but which one is negative? C is negative. You can see here at time T2, you can see red color and yellow color are positive, but whereas the blue color is negative. So which two currents are positive? A and B are positive. Which current is negative? Means C is negative. Is it clear? Confirm me once. Right. So I'm writing the same thing here. So here A is positive. So B is positive. So here C dash is positive. So they will cross, carry cross. I show the same thing here. Please see. So A is cross, A dash is dot. B is cross, B dash is dot. C dash is cross and C is dot. Why? Because we have seen. Then what will be the nature of those flux lines? It will be like this. Like this. Like this. You can see the North Pole here, the South Pole here. You can see the positions of the poles have been changed. From here, the poles have been shifted, right? Is it clear? Confirm? Confirm? Right. Now let us go for the third instant of time. What is the third instant of time? T3. T3. So can you please tell me which one is positive and which one are negative? Can you please tell me? Just type it. I want to see. So you can see at the instant of time T3. So which one are positive and which one are negative? Okay, I'll maintain the same speed. Don't worry. I'll go with the same speed. B is positive. A and C are negative. B is positive. A and C are negative. Excellent. 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 Right. Excellent. Excellent. Right. Very good. Enough. Thank you. So B is positive and A and C are negative. I'll show the same thing here. At the instant of time T3, only B is positive. A and C are negative. If A and C are negative, then what happened here? You can see negative means A dash will carry the current. Positive means B will carry the current. Negative means C dash will carry the current. So here it is cross. So I'll show the same thing for the instant of time T3. So here which one is positive? So here B is positive, whereas C is negative. Negative means this one. B is A is also negative like this. Then if you can see, correct? Is it clear? So which one is just one thing? Which one is positive here? Just 1 second. B is positive. A and C are negative. Correct. So here B is positive. Dot A is negative. So A is negative means just I have 1 second. Right. So negative means which conductor has to carry the current? Which conductor has to carry the current? Negative means A dash should be dot and B dash should be positive. So here B is positive and here A should be negative. Negative means, so this is cross, this is dot. C is also negative. So this is cross, this is dot. So these are the polarities of currents, right? So in the respective conductors of the respective phases. Once again, I repeat. So here at the instant of time T3, IB is positive, IC and IA are negative. So you can see here at the instant of time T3, IA is negative, IB is positive and IC is negative. As IA is negative, which one will carry the current? A dash. As IB is positive, which conductor will carry the current? B. and IC is negative, which conductor will carry the current? C dash. So it is cross. The same thing I'm showing here. So this is for instant of time T3. So like this. Then what will be the resultant of all this? The resultant will be like this. North, south. So this is the air where the rotor will rotate, please. So like this, you can see the poles are formed. Now let us go for the last instant of time. What is the last instant of time here? T4. So you can see at T4, IB and IC are positive, but whereas IA is negative. So at the instant of time T4, IA is negative, then IB and IC are positive. Negative means A dash will carry the current, B will carry the current, C will carry the current. So it is cross. I'll show the same thing here. So here in this case, like this, north, south. So you can observe here, with respect to time, what will be the nature of poles? Those are formed inside the stator core, they are rotating. As the poles which are formed inside the stator core are rotating, the flux lines which are passing through the air gap, so these are also rotating. You know, by definition, the group of flux lines, we call it as a flux. Even the flux in the air gap is also rotating. And such fields, we call it as the rotating magnetic fields. So yesterday or day one, if I'm correct, or day two, just I was discussing a huge theory to prove that with the three-phase windings and three-phase current, the nature of field is rotating. Just I was discussing a huge theory. What was the theory? We took three windings represented mathematically. We took three current represented mathematically. We passed those three currents. We had three individual MMF. We have seen the nature. Finally, we have took the resultant of those three and we got one equation and we have seen that the resultant is a rotating MMF. As that MMF is rotating, the field produced by such rotating MMF is also rotating, and we named that field as a rotating magnetic field. But fortunately or unfortunately, you can imagine by looking this. So tomorrow, if anyone questions you, Array, why that rotating magnetic field is formed in a three-phase means, you can see, Array, stupid fellow, when we are giving a three-phase currents to the three-phase winding, so a magnetic pole pair is formed if it is a two pole, and these poles will be continuously rotating in the core. Can we see with your naked eyes? No. But if you take a DC machine, the poles are projected. You can see the poles are projected or seen there. They are seen outside. So they are called as heteropolar. Why? Because the poles are seen outside. But whereas in case of the stator core of an induction motor, the poles will be hidden inside and they are rotating continuously with the time. As they're rotating continuously with the time, what will be the nature of those field means rotating magnetic field. So can I conclude like this? With the single phase excitation, those two poles are alternating. But when you are giving the excitation to all three phases, those two poles are rotating. So with respect to excitation, the nature of the design poles will be decided. With a single phase, those poles will be stationary, and with the three phase, those poles will be rotating. I hope this point is clear. Confirm me. Confirm me. Right. So can I give a statement? The nature of poles formed with a single phase winding and single phase currents are stationary and pulsating, but whereas the nature of poles formed with the three phase windings and three phase currents are rotating. As those poles are rotating, the field produced by such poles is also rotating, and such fields we call it as a rotating magnetic fields. Right. So this is what. So tomorrow in your engineering service examination or anywhere, if the question is asked, prove that with the three phase windings, three phase current, the nature of field is rotating, then you can go for the theoretical derivation which we had on first or second days, or you can go for this graphical derivation. So any of the things is valid. So this will give a clear picture that the poles which are formed inside the core, they are rotating, and field lines are also rotating, and such fields we call it as a rotating magnetic fields. I hope this point is clear. Raise the hands once. Right. So I'll give the statement here. I'll give the statement here. The nature of poles formed, once again confirm me, video, audio, structuring, everything is clear. No issue from my side, right? Right. So I'm writing. The nature of poles. So this yellow, when it is converting into white, this background, it is very dull. So we'll not take yellow, right? Please. This is also not that much fade. I'll take this. The nature of poles formed with three-phase windings. See, once again, I'm reminding you, whenever I'm using the terminology three-phase winding, please keep in mind that the turns per phase, the poles per phase, the space angle is 120. I will not repeat every time that three phase means this one. If any of these conditions is not like valid, we cannot call it as a balanced three phase winding. It may be something unbalanced. We are not going to talk. So in the last classes, when I'm talking about harmonic analysis, then we can see if a three phase supply is given to a unbalanced winding, means if these conditions are not satisfied, what will be the performance? That we'll see later, right? But as of now, in all the cases, we'll assume that whatever the three phase we are taking, it is a balanced winding. That means the conditions are the turns per phase, the poles per phase, the space angle between them is 120 degrees electrical. Keep that in mind. The nature of poles formed with the three phase windings and the three phase currents. Three phase currents. Again, when I'm talking about three-phase current, they are equally applicable. Purely sinusoidal, same peak value is purely applicable. Three-phase currents. The nature of poles formed with three-phase winding and three-phase currents are rotating. Rotating. As the poles are rotating, the field produced by such rotating poles is also rotating, and such fields are called, such field is called a rotating magnetic field. A rotating magnetic field. I hope it is clear. Confirm me, all of you. Raise the hands. Right. Done. Now, yesterday, when I was talking something about your so-called as a DC motor, if you just, I go back once. DC motor. So I told you that how the armature rotates. So just imagine like this. So I'm repeating once again DC. So whenever you are giving the excitation to the field windings, so these north and south poles are formed. Then at the same time, when you are giving the excitation to the armature winding, the south and north poles are formed. As soon as these poles are formed, they seize an opposite poles in the field, and to align that, this armature will try to rotate. But when this armature starts rotating, it looks like the position of those poles are changing. But due to the commutator action, the pole is appearing in the same place, and to align that same pole, the rotor or the armature will continues to rotate. It is something like this. This field pole is eagerly waiting that armature pole will come and align. So further, this armature is doing continuously work. It is rotating with a hope that it can align that south pole with this north pole. But there the commutator is cheating. It is changing the direction of current on the coil. when the conductors are changing their position and making the pole to appear in the same place, and hence that pole want to align, and for that this armature will be continuously rotating. So it is something like the poles are waiting to get aligned, but it is not possible. Why? Because commutator is changing the current, so this armature is continuously rotating. Is this point clear? Is this point clear? In other way, with respect to your Lorentz law, what are the conditions need to be satisfied? BIL. So how that first condition is being satisfied there with the help of a field coils and field winding currents. So B condition is over. What is the second condition? I need a conductor of finite length, where we are placing those conductors of finite length in the armature. And what is the third condition that need to be satisfied? Through that conductors, we need to pass a current. We are taking one more DC and we are passing the currents into the armature. So whenever that armature conductors are carrying the current, as they are under the magnetic field, those conductors will experience as a force, and because of that force, that armature will continues to rotate. Is it clear with respect to Lorentz law? Right. In other way, what may be the reason that the armature is rotating? So with respect to the field lines, I can tell. So when the armature conductors are not carrying any current, then the field lines are taking a straight path. But whenever that armature conductors are carrying the current, so because of those flux produced by that armature conductor, so the field paths are taking the longest path. So for that, there is a force exerting on the conductors to move, and hence that armature conductors will try to move. Is this point clear? Confirm me. Is this point clear? Confirm me. Right. So like that, your DC motor rotates. Now we have seen the formation of poles in the field, and also we have seen the formation of poles in the armature. Now let us see the formation of poles in the rotor circuit. Rotor circuit. Rotor circuit. Please see. So I have to go back to today's class. So we have seen the formation of poles in which core? Stator core. Now we need to see the formation of poles in the rotor core, right? Rotor core. Now for that you need some basics. Please try to answer to that basic questions. Please see. Some basic concepts. Please see. That is required here. Basics. See, I'm having a north pole. And because of this north pole, we are having the magnetic flux lines like this. Right? Done. And in this, I'm having one conductor. Like this. Let us assume that field is stationary, conductor is also stationary. When field and conductors both are stationary, so the flux lines are not cut, or the conductors are not cutting the magnetic flux lines, right? So both are stationary. So here what I am trying to do means I am trying to move the conductor. So here field is stationary. Please answer this. Field is stationary and conductor is also stationary. Also stationary. No flux cutting and no EMF in the conductor. Will agree? Please tell me, will agree all of you? Right. Now what I'll try to do means I call this one as some position T0, and I'll take one position T1. So there what I'll try to do means the field is stationary, but the conductors are moving. So this is a field which is stationary, and in this I'll take a conductor. You can see the position of the conductor. It is coming side cross. See, Shraddha Chavan. So is there any technical issue? No, it is. So please, so everything is clear. Everything clear? Raise the hands once. All right, done. See, if any questions, I'll see later. Just raise the hands only to confirm if everything is clear, please. Right. So here, the field is stationary again. Field is stationary. See, once again, I'm reminding you, please raise the hands only if you have any technical issues. For question and answers, I'll spend time, don't worry. Even yesterday, after the class is over, as I have given my mobile number to some of the students have called me, even have answered to their questions also. So I'll be readily available to the students. It is not only during the question and answers I'll be answering. No, if you are not getting a chance or if I'm unable to catch your raising hand, then you can call me a number, 100% I'll answer. No issue in that. Please keep that in mind. So please raise the hands only for any technical issues. For technical questions, use the question and answer session or use mobile for the answers. Please remember, right? So here field is stationary, but conductor is moving. Conductor is moving. Conductor is moving. So you know that, so flux cutting is taking place, flux cutting, and hence EMF is induced. EMF is induced. Agree? Confirm? Agree? Raise the hands. Right. Now I want to know the direction of induced EMF in this conductor A. So if I want to know the direction of induced EMF, which rule I need to call upon? Fleming's right hand rule. So I'll be assuming the Fleming's right hand rule here. See. So the field is downwards. The conductor is moving in clockwise direction. This is the field. And what will be the direction of induced EMF? Right hand if I apply. So it is cross. It is cross. So here you will not get. So it is cross. So the direction of induced EMF in that conductor is cross. It is into. It is cross. Is this point clear? Is this point clear? Right. Only few. What happened to others? Please, all of you. Right. It is something like this, Baba. I'll be assuming these are the field lines and this is the conductor. You can see only the circle. Here you can see only the circle. So the field lines are stationary, the conductor is also stationary. When both are stationary, there is no flux cutting. But when I move this conductor, move this conductor, so this moving conductor is cutting the stationary flux lines. Moving conductor is cutting the stationary flux lines, and hence what is induced in that conductor? EMF is induced. So can I write here? Here, the moving conductor is cutting the stationary flux lines. Is cutting stationary flux lines. And hence an EMF is induced. So what is the nature of that induced EMF? What is the polarity of that induced EMF? Cross. I hope this point is clear. Now I'll take one more case. In the second case, the field is moving, the conductors are stationary. It is only 10% charge. Just 2 minutes. I'll not take much time, 2 minutes. So that is 10%. Otherwise that will go down, right? Right. So I'm back now. See, in the second case, so in the first case, what is happening? I'm taking this one are the field lines and this is the conductor. So which one is moving? Conductor is moving. So when the conductor is moving, you can see the conductor is cutting the stationary flux lines. In the second case, this conductor is stationary, but the field lines are moving. Field line is moving, the pole is moving, the field lines are moving. Even in the second case also, there is a question of flux cutting. Why there is a question of flux cutting means, so in the second case, the moving flux lines are cutting the stationary conductor. So according to Faraday's law, so Faraday's law never said that only the moving conductors has to cut the stationary flux lines. It can be the conductor may be stationary, the flux lines may be moving. In both the cases, an EMF will be induced, right? Is this point clear? Confirm me. Right. So what I'll do means in the second case, in the second case, the pole is moving, moving, but whereas the conductor is stationary. So it is moving field, and stationary conductor. Stationary conductor. So in the second case, can I write like this? Please help me out. Can I write like this? In the second case, the moving flux lines are cutting the stationary conductors. Moving flux lines are cutting the stationary conductors. And hence an EMF is induced. Is it clear? Confirm me. Is it clear? Right. Now I need to find out the direction of induced EMF here. If I need to find out the direction of induced EMF, we have learned that the definition of Fleming's right hand rule is stretch the first three fingers of the right hand mutually perpendicular to each other. Point the forefinger in the direction of field, thumb in the direction of motion of the conductor. Then the middle finger gives the direction of induced EMF. The statement itself says that the thumb should be in the direction of moving conductor, motion of the conductor. But very unfortunately, in the second case, the conductor is stationary. So if the conductor is stationary, is it not possible to apply Fleming's right hand rule? No, even in the second case also it is possible to apply the Fleming's right hand rule. How? Means I'll take a small example. Say you are sitting in one bus and next to you there is one more bus. Both the buses are in the bus station or bus stop, right? They are stationary, right? They are about to leave, but they are stationary. So you are sitting in one bus. Then as the buses are still not moving, the stationary, you started playing with your mobile, But during that time, what has happened is the bus which is next to you is moving in forward direction. Then if you see that bus at that instant, you feel that your bus is moving in opposite direction. It is an illusion that you feel that because that bus is moving in the forward direction, at that instant you feel that you are moving in opposite direction. But truly speaking, you are stationary, but because of the bus which is moving in the forward direction, the bus which is next to you is moving in the forward direction, you feel that you are moving in the backward direction or opposite direction. Is this point clear? Right. So here also the same logic I need to apply. So here the field system is stationary. The field system is moving. The conductor is stationary. Then if you want to know the direction of induced EMF, in this particular case, you have to imagine that the conductor is moving in a direction opposite to the direction of magnetic field to apply the Fleming's right hand rule. But truly speaking, the conductor is stationary and the field is moving. Once again, I'm repeating and revising. Imagine that you are sitting in one of the bus and that bus is stationary. And next to you, there is one more bus. Both the buses are stationary. As both the buses are stationary, you are started working or playing with a mobile. So during that time, what has happened is the bus which is next to you is started moving in forward direction. Then at that instant, if you see that bus, you feel that you are moving in opposite direction. But truly speaking, you are stationary, and because of the bus which is moving in the forward direction, you feel that you have an illusion that you are moving in opposite direction. So here also, if I want to apply the Fleming's right hand rule, as the conductor is stationary, as we know the definition for Fleming's right hand rule is the thumb should be in the direction of motion of the conductor. So to apply that, we have to imagine that the conductor is moving in a direction opposite to the direction of magnetic field. But truly speaking, the conductor is stationary, the field is moving. As the field is moving in clockwise direction, we imagine that the conductor is moving in a counterclockwise direction. Is this point clear? Confirm me. Right. So here I'll write a note. Here, here, as the conductor is stationary, and moving, field is moving, to know the direction of induced EMF, induced EMF, induced EMF, we have to consider that, the conductor is moving, in a direction opposite to the field, But truly speaking, the conductor is stationary. Is it clear? Confirm me all of you. Is it clear? Confirm me all of you. Right. So in this case, in which direction the field is moving? The field is moving in clockwise. Then we have to assume that the conductor is moving in counterclockwise direction. But not practically it is moving, it is stationary only. Then I need to know the direction of induced EMF. According to your Fleming's right hand rule, what is that? Field is downwards. The conductor is assumed to be moving in counterclockwise direction. Then what will be the direction of induced EMF? It is outwards. Outwards means it is, in this case, dot. The direction of induced EMF will be dot. It is dot. Is it clear? Confirm me. Is it clear? Confirm me all of you. Right. Sir, why we need to discuss all these things? Yes, I tell you one thing, right? See, I'll explain this. So all this is required to know the concept of pole formation in case of your induction motor in rotor circuit. So it is true that we have a three-phase designed winding in the stator, but in the rotor, we don't have winding in case of squirrel cage, we have only bars. So how the poles are formed, that I'm trying to explain now, right? Please try to understand this. See, Baba, you believe it or not, all these concepts are required to understand the working principle of an induction motor. You know, out of my this 15 years of experience in teaching, particularly in machine subject, I was being called by many of the colleges for a faculty selection, recruitment process. So the fundamental question which I ask to most of the faculty who are coming for these interviews to teach for you people, can you please explain the working principles of a motors, DC motor, induction motor, synchronous? Please tell me how the rotor rotates. Tell me that. This is the basic question which I ask. You know, 80% of the person who are coming for the interview fail to answer this question. The simple definition, the statement what they give, the magnetic field lines will cut the rotor conductors and EMF is induced and hence the rotor rotates. This is the statement. This is the para which they used to by heart and they used to tell. So 80% I have seen like that, but we are not going to see that, right? Fine. So what is the direction of induced EMF means? The direction of induced EMF is outwards. I hope this point is clear. Now I'll be explaining the concept of pole formation in case of a rotor, and I'll explain how the rotor of an induction motor rotates. Just like if you imagine in case of a DC motor, the armature is rotating to align the armature poles with the field poles. Further, the armature is rotating. That means the machine develops the torque to align the armature poles with the field pole. For that, it develops the torque. Now let me explain in case of an induction motor how the rotor rotates, right? Please see here, please. So here, so all are following the class, raise the hands, all are following the class, right, done. I'll take the stator here. So this one is the stator. I'm not showing any of the windings, any of the coils, any of the conductors. Just I'm imagining that there are two poles here. How many poles are here? Two poles, north and south poles. So because of these poles, we'll be having magnetic flux lines. And these magnetic flux lines will be traveling from north to south, right? Then I'll be taking the rotor here. A rotor here. A rotor here. See that this much air gap will not be there. Just to make you understand, I have drawn larger air gap, but no larger air gap. So here we'll be having conductors. So here we'll be having conductors. So these we call it as rotor bars or rotor conductors. Like this, right? I'll draw that rotor separately, even separately. I'll try to draw that rotor so that you can understand. Like this, right? This is the rotor. So as of now, I pre-imagine that even the rotor is also made up of a magnetic material, laminated silicon steel. So again, I'll spend some 2 to 3 hours on that in the coming days. Don't worry, don't worry. Now you please tell. So whenever a three-phase excitation is given to the stator winding, I'm not drawing those windings and other things. Please understand. IA, IB, IC, what are formed in the stator core? Poles. Can we see with our naked eyes? No. What is the nature of these poles in the core? Rotating. So with what speed those poles will be rotating? Ns. As these poles are rotating, even the flux lines will also rotate, right? Now you can see if I'm imagining this one as the pole and these are the rotor conductors. As these poles are rotating, as these poles are rotating, as these poles are rotating, so they are cutting the stationary conductors. Which conductor? Rotor conductors. So can I say the formed stator poles which are rotating are cutting the stationary rotor conductors. As of now, the rotor is stationary. They are cutting the stationary rotor conductors. As a result, what is induced in the rotor conductors? And EMF is induced. Is it clear? Confirm me. Is it clear? Confirm me. So once again, I'm imagining these are the flux lines produced by the stator poles.
I'm having a rotor, and on the rotor I'm having a conductor like this. What is the nature of these poles in the stator core? Rotating. As these poles are rotating, they are cutting the stationary rotor conductors. So due to this flux cutting, what is induced in that rotor conductors? An EMF is induced. Why you people are texting? Is everything correct? Right. Yes. Okay. Fine. Fine. So can I say, can I write a note here? Rotating flux lines, flux lines are cutting the stationary rotor conductors, and hence EMF is induced in the rotor conductors, in the rotor conductors, right? So an EMF is induced in the rotor conductor. Is it clear? Confirm me all of you. All right. Now I want to know the direction of induced EMF. If I want to know the direction of induced EMF, I told you that we need to apply Fleming's right hand rule. So if I need to apply Fleming's right hand rule, the conductor has to be moving, but very unfortunately here the conductor is stationary. If the conductor is stationary, it doesn't mean that we have no rule to find out the direction of induced EMF. Already I told you that in that particular case, we have to imagine that the conductor is moving in a direction opposite to the field. So in this case, you can see, if I consider one conductor here, A conductor. So with respect to that A conductor, I'll find out the direction of induced EMF. Field lines are downwards. Field is downwards. The field is moving clockwise, but we have to assume that the conductor is moving in counterclockwise direction to apply the direction of induced EMF. Then what will be the direction of induced EMF? Dot. So it is dot. So in all these conductors, we'll be having dot. At that instance, we'll be having dot. Is it clear? Is it clear? Confirm me. I told you already this. Right. It is dot. If that is the case, what will be the direction of induced EMF in these conductors? It is cross. It is cross. So the polarities will be like this. But what will be the magnitude of that induced EMF? Please tell me like this. Please tell me. Please tell me. So I want to know, just I will number this. Please help me out. So why I have taken dot? See, please help me out. I'll be numbering this. Please see. I'll be numbering this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. If my question to you people is, are among all these conductors with this position, in which conductor the EMF will be maximum, whether in conductor 1 or conductor 4 or conductor 5. For that I'll tell you in which conductor it is maximum. So I will plot the direction of or the nature of the induced EMF. Please see. So here it is dot, 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 cross, 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 cross. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I'll just draw this. Please hold. Baba, these are all like important points to be done. So this is conductor 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, again 30. Numbering 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So if my question is, let me see, anyone will answer. So this is like this you have given. So the field is rotating. Now at this instant, So the position of the field is like this. Then among this 1 to 14, which conductor will be having a positive peak and which conductor will be having a negative peak? If the question is asked like this, which conductor will be having a positive peak and which conductor will be having a negative peak? So please try to answer to that question. Otherwise, I'll explain which conductor will be having a positive peak and which conductor will be having a negative peak. Conductor 4 and conductor 10. 4 and 10. 1 and 7. Only few people have answer. 1 and 7, 4 and 10, 1 and 7, 1 and 7, 1 and 4, 4 and 10, 10 and 4. Okay, whatever, maybe 7, 1 and 7, 1 and 7, 4 and 10, 1 and 7. Okay, so it is like most of the people are turning 1 and 7 and 4 and 10, like mixed answers I'm getting. So 50-50, I'll answer, please. Now don't tell, don't text, don't text, don't text. See, here, which two conductors will form one coil means, so this 1 and 7 will form one pair. Why? Because 180 degrees. 1 and 7 will form one pair. Similarly, 2 and 8 will form one pair, one coil. Like that, 4 and 10 will form one pair. Now the question is, in which conductor or in which conductors the EMF will be maximum? If you remember, EMF is not due to the magnetic flux lines which are passing through the coil, but EMF is due to the changes in flux lines. If maximum flux lines are passing, EMF is zero. If those changes are maximum, the EMF is maximum. What do you mean by that? I'll explain. See, I'm having a north pole like this. And say because of this north pole, we are having magnetic flux lines. 1, 2, 3, 4, 5. If anyone questions how many flux lines are coming out of that north pole means, I can say blindly 5. Now I'm having a coil like this. Coil like this. Coil like this. So the magnetic flux lines are like coming and I'm having a coil legs. So if the coil is like this, then you can see all the flux lines are passing through the coil. So the flux linkages are maximum. Will you agree with me? Why? Because you can see the conductors are like this and they are collecting all the flux lines through that. So the flux linkages are maximum. What is the meaning of flux linkages? The number of flux lines passing through the coil represent the flux linkages. If the coil conductors are like this, then you can see the flux lines are maximum. They are parallel. So all the flux lines are passing through that. Is it clear? Is it clear? Only few, what about others? I need the raise from all the hands. All should raise the hands. So now with respect to this position, which two conductors of a coil are carrying all the flux lines? You can see this is conductor number 1, this conductor number 2. You can see these two conductors are like this, and through that all the flux lines which are produced by the north poles are passing. That's the reason there is no EMF here. There is no EMF here. There is no EMF here. But when I move this coil like this, when those two conductors are coming like this, then you can see the number of flux lines passing through this coil are 0. If I make this coil to move like this, so this is a north pole. If I move this coil like this roughly, all the flux lines are flowing down. So there are no flux lines passing through that. That means initially how many flux lines were passing? 5. But when you move this coil perpendicularly, there are no flux lines passing. So in this, in which coil there will not be no flux lines passing? In 4 and 10, there will not be any flux lines passing. But when the same coil 4 and 10 is coming like this, 5 flux lines were passing. But when the coil is moving like this, so there are no flux lines passing. So at which instant of time the coils are not carrying any flux lines means when the conductors are coming like this. So which conductors are coming like this? So you can see 4 and 10 are exactly below to the north pole and below to the south pole. I can say there are no flux lines passing, but when the same coil is like this, 5 flux lines are passing. So when they are coming like this, the flux lines are 0, the changes are 0, 5 minus 0. So 5 flux lines are not passing through that coil. So the changes are 0, the EMF will be maximum. The changes are maximum. The EMF will be maximum. Is this point clear? Is this point clear? So here can I say, with respect to this simple observation, the conductors which are coming under the poles will have maximum EMF. The conductors which are at an angle of 90 degrees will have zero EMF. When the conductors are at an angle of 90 degrees, they are carrying all the flux lines. When the conductors are coming under the poles, they are carrying no flux lines. The changes are maximum. The EMF will be maximum. Is this clear? Confirm me. Raise the hands. Right, done. So here you can see. So if I'm going to plot here, so which conductor will be having maximum voltage? 4 in positive direction, and which conductor will be having maximum voltage in negative? So it is 10. I'm plotting that. So here 4 will be having maximum voltage and 7 will be having, not 7, 10 will be having maximum voltage. 1, 2, 3, 3. So like this, the remaining things will have less voltages. Why? Because there will be little changes. So these are the, so some textbook call it instantaneous bar voltages. Why? Because those magnitudes will depends upon the changes in flux lines. You can see roughly I'm trying to draw like this. So this is for one cycle. So what is the nature of that induced EMF? It is AC. Conductors will carry AC current. Is it clear? Confirm me. Confirm me. Right. So here, can you please tell me? Can you please tell me? In case of rotor, we are not giving any separate excitation to the rotor conductors or rotor winding. But whatever the EMF that is induced in the rotor conductors is due to the flux cutting action of the stator poles flux lines. So whatever the flux lines we have due to the rotation of the stator poles, those flux lines are cutting the stationary rotor conductors, and hence an EMF is induced. But at the same time, the magnitudes of those induced EMF in that particular conductors will not be same. So those magnitudes will be different. So the conductors which are cutting maximum flux lines will have more EMF when compared to the conductors which are cutting less number of flux lines. So you can see 1 and 4, 1 and I don't know numbers, 1 and 7. So they are not cutting any flux line. The EMFs are 0. But the 4 and 10, they are cutting maximum flux line. The EMF will be maximum in that. Is it clear? Confirm me. Right. Just 1 second. 1 second. So 1 second. Just my mother brought tea. I'll have tea. 1 minute. Just not even 1 second. 1 minute. I'll just. Right. Done. I'm back. So due to flux cutting, an EMF is induced. Is it clear? Confirm me, all of you. The polarities are clear in the rotor circuit. Confirm that once. The polarities are clear in the rotor circuit. Confirm me once, all of you. Once again, raise the hand for my convenience. Right. Done. The polarities are correct. Now please remember, in case of an induction motor, right. So in case of an induction motor, the rotor circuit will be always closed. It is something like this. If I'm having a conductor, if this conductor is not cutting any flux lines, so there is no EMF. But when this conductor is cut by the magnetic flux line, there will be an EMF. So it is acting as a battery. I've said 2 volts assume. So I will not call it as a conductor, but I'll call it as a battery of small voltage induced. Why? Because it is cutting the conductor. And if you close this circuit with some small resistance, then what happened to that EMF will establish as a circulates a current in that. Will agree with me? Will agree with me? Right. So in case of an induction motor, the rotor bars are short circuited on either side with end rings. We'll see this, don't worry, are short circuited with end rings on either side. So due to this, what is induced in this? And a current will circulate. So remember that current is induced current. Why the name induced means that current is due to the induced EMF. So that's the reason it is induced current. So you can note the difference between the currents which are flowing in the stator conductor, the currents which are flowing in the rotor conductors. The currents which are flowing in the stator conductors is due to the supply current, but whereas the currents which are flowing in the rotor conductors are due to the induced EMF, right? So these are called as induced currents, right? Is this point clear? Right. Now the rotor circuit is closed, current circulate. So if anyone questions you, Arey, how these stator poles are formed, I tell it is due to the stator conductors and stator currents. If that is the case, rotor is also having rotor conductors and rotor induced current. Because of that, there is one more flux. Yes, there is one more flux. I want to know the direction of flux lines. For that, which rule I need to call upon? Fleming's right hand rule. Sorry, right hand thumb rule. Very extremely sorry, right hand thumb rule. So if I'm applying that, you can see here, the flux lines will be like this. You can see the current is coming out. Dot means out. If I apply the right hand thumb rule, we can see it is in like this. Like this. And if I apply here, like this, right? Is it clear? The direction of rotor flux lines, is it clear? Please tell me. All right. Now you can see whenever we are having magnetic field lines, those magnetic field lines are due to the magnetic poles only. Then I need to find out what is the pole on conductor 1 and what is the pole on conductor 7. Then for that, you know that if the magnetic flux lines are traveling from core to air, what is the pole that is formed there? North. Already we have seen. If it is from air to core, what is the pole that can be formed there? South. This is already we have seen. Then you can see this is the air. You can see this is the air, and these are the direction of flux lines. So the magnetic flux lines are traveling from air into core. So from conductor 1, they are traveling into core, from air into core. So from air into core means what is the pole that can be imagined there? A south pole. And as the magnetic flux lines are traveling from core into air from conductor 7, I'm calling it as a north pole there. So like this, a south pole is formed here and a north pole is formed here. Is it clear? Confirm me all of you. Is it clear? Confirm me all of you. Right. Right. Then as soon as this south and north poles are formed, immediately, very immediately, what happened means, this south pole will see a north pole here, and this north pole will see a south pole here. At the same time, this south pole will see a south pole here, this north pole will see a north pole here. So these rotor poles, they seize an opposite poles in the stator core. These rotor poles, they seize an opposite poles in the stator core. To align these rotor poles, the rotor starts rotating. Why? Because this is a south pole, this is a north pole, there is a north pole. To align this south pole with this north pole, this rotor starts rotating. But those poles says that we are already running, you catch me. Now as these stator poles are rotating, to align the south pole of the rotor with the north pole, even the rotor will also start rotating. I'll use one terminology, the rotor chases. To align the rotor poles with the stator pole. Why I'm using the terminology chases means the stator poles are rotating, they're running. To align this rotor poles with that stator pole, the rotor chases. It is something like a boyfriend and girlfriend. So a boyfriend always chases a girlfriend, just only for kidding, right? So like this, the rotor will also chases the stator poles to align the rotor poles with the stator poles. Like this, the rotor will start rotating. So the rotor rotates. Here also, can I use one statement? The rotor rotates to align the rotor poles with the stator pole, and hence the rotor starts rotating. So it starts rotating. Is it clear? Is it clear? I need all of you to raise the hands if it is clear. Right. So here, in case of an induction motor, the rotor rotates to align the rotor poles with the stator pole. Can I imagine like this? See, whenever a three-phase supply is given to the stator, what are formed in the stator core? Poles. As this pole starts rotating a small fraction, if they starts rotating, they cut the rotor conductor, EMF, current, or rotor poles. They see certain opposite poles in the stator to align that the rotor will start rotating. It is something like a mechanism. What is that mechanism? Stator pole starts rotating, cutting the rotor conductor, EMF, current, rotor pole. They see some opposite poles there to align that the rotor will start rotating. Is this point clear? Confirm once again. Right? So here the rotor will rotate like this. So here the rotor is chasing the stator poles to align the rotor poles. So can I write a statement here? In this case, in this case, in this case, in this case, the rotor chases. I'm using the terminology chases. Rotor chases the stator poles to align the rotor poles with the stator poles, with the stator poles, with the stator poles. But here there is no chance that the rotor can rotate with that stator pole speed. Why? We'll see in the complete working principle. It is only a partial explanation. I hope this point is clear, right? Please confirm me lastly, like this the rotor poles are formed. So I want to give one statement. What is that statement? If any conductor is under a magnetic pole, the voltage induced in that conductor will be maximum. I cannot say always dot or cross, basing on the direction of the field. For example, see, here the field is rotating clockwise direction, then it is dot. If the field is rotating counterclockwise direction, it may be cross. But I want to say that if any conductor which is coming or which is exactly under one pole, which is in motion, when the fields are under motion, at a instant of time, one conductor is coming exactly under a pole. In that conductor, the EMF will be maximum. The conductor voltage will be maximum. Is this point clear? Confirm me. I'll write that point. Right. So can I write? If any conductor is coming under a rotating pole, then the EMF induce in that conductor is maximum. I hope this is clear. So like this, the rotor poles are formed, right? So this is the concept of pole formation in case of a induction machine. Synchronous machine, your teacher will explain. I'm not explaining that. So this is the concept of pole formation in case of induction motor. Finally, raise the hands once. Finally, if you clear with this, then you may have a doubt, sir. You have explained only 2 poles per phase. Huh? Sir, I want to design 4 poles per phase. Can you please explain? Yes. Sir, I want to design 6 poles per phase. Can you please explain? Yes. Sir, I want to design 10 poles. Yes. So for that, what I'm trying to do is I'm trying to explain for 4 poles, and I'll explain the logic in that. You please try to get the logic, and you can apply the same thing for any number of poles, right? Please see, for 4 pole, let me explain. For 4 poles, design of 4 poles per phase. Once again, I'm reminding you, All these concepts are required in our coming classes. Please keep that in mind. That's the reason I'm just pulling everything now. Design of 4 poles per phase. 4 poles per phase. Now, for that, I'll take 2 coils. What are those 2 coils? Let me take here. So for 2 poles, I took 1 coil. For 4 poles, I need to take 2 coils. This is 1 coil with singleton. This is one more coil with singletons. Coil 1, coil 2. So how many coils we have taken? 2 coils. I have joined these two. They are connected in series. And to this, I am giving a AC excitation. Which excitation I am giving? AC. AC excitation I am giving. Right? So during positive half cycle, what happened? If this is A, this is B. During positive half cycle, what happened? You can see, let me call conductor A1, A2, A3, A4. So during positive cycle, so you can see A will be at high potential. Conductor A will carry, A1 will carry the current, A2 will return the current, A3 will carry the current, A4 will return the current. Is it clear? Is it clear? Right. Now I'll show the same thing in the stator. Same thing in the stator. So in this case, how many conductors we need per phase? 4. But there in the previous case, how many conductors we need per phase? 2. Why? Because it is 2 poles. So here we need to take 4. Right? 4. 1, 2, 3, 4. So this is A1, A2, A3, A4. Right? Now you can see A1 is carrying the current into, and A2 is outwards, A3 is into, A4 is outward. Is it clear? Is it clear? Confirm me. Right. Now I need to draw the direction of magnetic flux lines. So which rule I need to call upon? The same right hand thumb rule. Like this. Right? That. Then if you can see here, this is core. The magnetic field lines are traveling from core into air. Core into air. North pole. The magnetic field lines are traveling from air into core. South pole. The same magnetic field lines are traveling from, you can see this is the direction. North pole. This is the south pole. So how many poles are formed here? 4 poles. How many coils are required? 2 coils. For example, if I want to design 6 poles per phase, then I need 3 coils. 3 coils. Then accordingly you can have 6 poles. If I want to design 8 poles, then I need to have 4 coils. Accordingly you can design 8 poles. Is this point clear? Confirm me. Is this point clear? Confirm me, all of you. Right. So this is with respect to your phase A. If you want to go for phase B, then with respect to A1, after 120 degrees electrical, you have to place B1. Similarly, with respect to A2, after 120 degrees, B2. Like that you can. Similarly, C1, with respect to B1, 120 degrees C1, like that you can place, which is not required here. I hope this is clear. So this is for how many poles? 4 pole stator. Is this point clear? Is this point clear? Right. Then what I will try to do means, I'll try to change the end connections. So these are called as end connections. Already you know. These are called as end connections. Back end connections. End connections. You can see here, A1 is joined with A2 and A3 is joined with A4. Now I'll change the end connection. What do you mean by that? I'll connect A1 with A3 and A2 with A4. Then what happened? You can see here between A1 and A2, there is one pole N1, and between A2 and A3, there is one pole S1, N1, N2, S2. How many poles are formed here? 4 poles are formed. Now I'll change the end connections. If I change the end connections, what happened? Let us see. So this point will make use. Please remember. I'll take the same circuit. I'll change the end connections. So front end I'm not changing, back end I'm changing. So this is A1, A2, A3, A4. I'm changing the end connections. You can see I'm changing the end connections. I'm changing the end connection. If I change the end connection, then in the same stator core, how many poles will form? We'll see. Let I'll take the same stator. See one announcement. So one small announcement to all. So tomorrow my class will not be there, right? I have some emergency work. So tomorrow I cannot take the class. So for the batch which has started on 5th July, recent batch. So for them, there is no class tomorrow. But for the previous batches, which already started earlier, previous batches, old batches, so for them, you have power systems, faults and stability, some pending topics are there. So for them, tomorrow, 5 to 9, there will be class for them. For only old batches, there will be class, but new batch, there is no class for tomorrow. Day after tomorrow, again, we'll have the same schedule, 5 to 9. So Sunday, we have the same schedule. Only tomorrow, we don't have class. So Sunday, the class will be again back. Is it clear? Confirm me. All right. But for tomorrow, old batches will have the power systems class. 5 to 9, the power system class will be there. For other batches, right? Please. Done. And Sunday, again, I'll come back. And again, 5 to 9, please. And one student today, he has requested, I don't know which batch student he is. Sir, you can increase the time. So this that power I don't have. So if everyone is willing, so I'll inform to the manager so that he can schedule the class instead of 5, 4, like that. We'll see that that is not in my hand. So I speak to him, I'll come back to you. Don't worry, right? Please. So from your side, you have any objection if I start the class from 4 instead of 5? All of you raise the hands. You have no issue. I can take. Right. I speak to them. I'll come back to you. Right. Fine. So this is conductor A1, A2, A3, and this is A4. Now, say during the same positive cycle, you can see whenever I'm changing the end connection, what happen you can see. So this A1 will carry the current, A3 will return the current, A2 will carry the current, A4 will return the current. So whenever you are changing the currents, you can see the currents in the two consecutive immediate conductors are changing. If you look here, A1 and A2 are carrying opposite currents, but here A1 and A2 are carrying the same currents. Why? Because end connections have changed. If that is the case, what happened? Let us see. So here both are carrying into. 1 second. Sorry for the disturbance. So there is an important call. So excuse me for that. Right, fine. I'm back. Just excuse me. So some disturbance I had, right? Right. So I think you are back. So we'll take break after this. See, so what I have done is I have now please raise the hands if everyone is present. Raise the hands once. Right. Now when I have changed the interconnections, you can see the direction of currents have changed. You can see here it is cross. This is also cross. This is dot, and this is also dot. Right? You can see both the directions are into and both the directions are outwards. Then if I'm trying to draw the direction of magnetic flux lines, it is like this. It is like this. It is like this. Then you can see this is a north pole, this is a south pole, right? I'll not attend, don't worry. Just I'll keep it in mute. Right. Done. This is north pole and this is south pole. Then you can see in the same stator, how many poles were formed earlier? 4 poles. But how many poles are formed now? 2 poles. So can I say like this? By changing the end connections, we can change a p pole machine into p by 2 pole machine. So here, for the same 2 coils, how many poles we have formed? 4 poles. And for the same 2 coils, how many poles are formed? 2 poles. So by changing the end connection, we can change a p pole machine into p by 2 pole machine. Is this point clear? Confirm me all of you. Is this point clear? Confirm me all of you. Right. So remember, this concept of pole changing will make use in case of a speed control techniques. So tomorrow, when I'm talking about the speed control technique, so I'll tell that tomorrow means not immediately tomorrow, after some days. When I'm talking about the speed control techniques, I'll say that by changing the end connection, we can change a p pole machine into a p by 2 pole machine. Then how means don't ask, you have to come back to this point. I hope this is clear, all of you. Confirm with me. Confirm with me. So if I represent the same thing here, you can see here, already I told you, see, as these 2 conductors are carrying the currents in the same direction, there are no flux lines here. Or in other way, I'll try to elaborate more. Please just give me 1 minute time. Right, like this. So this is the flux. This is the flux. This is the flux. This is the flux. Then if you can observe, between A and A2, one side the flux lines are like this, on the other side the flux lines are like this. Then you can see they are cancelling out. There is no pole formation. Here, between A2 and A3, one side the flux lines are like this, on the other side the flux lines are also like this. That means the flux lines are traveling from core into 8. There is a north pole. So here, one side it is like this, on the other side it is like this. They are cancelling out. So here also the flux lines are traveling from core air into core. This is a south pole. So initially, how many poles were there in that core? 4. How many poles are there now? 2. Right. So can I say, if 2 conductors, 2 consecutive conductors, here you can see, if 2 consecutive conductors, if they are carrying the currents in opposite direction, there exists a pole. If the 2 consecutive conductors, they are carrying the current in same direction, there is no pole here. You can see there is no pole here. N, there is no pole. This is south. So can I finally say a p pole machine can be converted into a p by 2 pole machine by changing end connection, right? So I'll continue on this because it is almost 7:16, so long back. I'll take some break and I'll revise something on this. Again, I'll proceed. Is it clear? Confirm me, all of you. Raise the hands. Right. So I'll take break. So I'll come back in 20-25 minutes, right? Please.
Right, I'm back. Right. Right. All of you, please confirm me if you are clear with my video, audio, screen movement, and other things. Right. So I'm trying to highlight few points with respect to this pole formation. Right. So what are those points? Means see. First point is first point is first point is if you look at any numerical or any nameplate details, so on the nameplate details, you can find the information about poles, 4 poles, 6 poles. So whatever the information that is given in the numerical or in any nameplate details, it represent the stator poles per phase, right? So can I say if P pole, induction machine means P number of poles per phase. So please keep that in point. It is per phase. The other thing is, if you want to design the poles, you need to take care of few things. What is that? See, if the two consecutive conductors means side by side conductors. If the two consecutive conductors, side by side conductors, you can see A1 and A2 are side by side conductors. If the two consecutive conductors are carrying the currents in opposite direction, you can see in opposite direction there exists a pole. There exists a pole. Similarly, if the two consecutive conductors, side by side conductors, if they are carrying the currents in same direction, there is no pole formation. There exists no pole, right? I think this point is clear. If two consecutive conductors, side by side conductors, if they are carrying the currents in same direction, there is no pole. If they are carrying the currents in opposite direction, there exists a pole between them. Please confirm if it is clear. Right, done. I write the same point. Second point is if the two consecutive conductors are side by side conductors carries the currents in opposite direction, there exists a between them pole between them pole between them. I think this point is clear. Confirm, all of you. Right. Next point is if the two consecutive conductors, if they carry the currents in same direction, there exists no pole. There is no pole form. If the two consecutive conductors carries the currents in same direction, there is no pole formation. There is no pole formation. I hope this point is clear.
Fourth point is a p-pole machine can be changed into a p by 2 pole machine by changing end connection. I'm reminding you once again, this logic, this concept I'll be using in speed control techniques. Why? Because we are going to see in the coming days that by changing the stator poles, we can change the number of poles, right? And the speed, sorry. A p-pole machine, a p-pole machine can be changed into a p by 2 pole machine by changing end connections. By changing end connections. So our induction machines are told that a p pole machine can be changed into p by 2 pole machine. So I can change 4 pole to 2 pole, correct? 8 pole to 4 pole, correct? 6 pole to 3 pole, no. 3 poles to 1.5, no. Please remember, a even number can be changed into a other even number, but not like even to odd or odd to fraction. Please keep that in mind, right? So in this, I'll write even to even. Even to even. Is this point clear? Confirm all of you. Confirm all of you. Right. So this is something about the concept of pole formation. So finally, we proceed with the other concept, new concept. Let me once again revise and recap. So we have seen why we need two magnetic fields and why the relative speed between the two magnetic fields has to be zero. So if the relative speed between the two magnetic fields is zero, then the poles of the respective fields are stationary, then there may be a continuous attraction and repulsion due to which there is a continuous rotation. Similarly, for the production of torque, the stator and the rotor pole should be same. Otherwise, the attractive and repulsive forces, they are going to cancel out and there is no concept of torque production. So this is something about the concept of pole formation. Next one is C. In this analysis, I have considered only a coil with one turn. You can see there is a coil with only one turn. We have considered with only one turn. But fortunately or unfortunately, if you open any machine, you don't have a coil with one turn. You'll be having a coil with more than one turn. If I'm having only one turn, then you can see I can place only one conductor in one slot. But if I'm having more than one turn, then in that case, I need to place more than one conductor. Why? Because for example, if I'm taking a 3-ton coil like this, like this, then I need to place these three conductors on one side and these three conductors on another side. Then how to place those three conductors, right? So there are two possibilities. One is concentrated winding. The other one is distributed winding. So the next concept is whatever the discussion we had, we took only one turn. But generally, we don't have only one turn, we'll be having more than one turn. So if the conductors are more, if the turns are more than one turn, how to place the conductors in the stator slots? I hope this point is clear. Confirm all of you. Right, done. Next one is placing of placing of placing of stator conductors in the stator slots. In the stator slots, right? What do you mean by that? So for that, what I'll do means I'll consider a coil with 3 turns. A coil with 3 turns. So whenever I'm talking a single coil, it is designed for 2 poles. Please, we are going to learn many things here, please.
right? So this is a coil with how many turns? 3 turns. Coil with 3 turns. 3 turns. I call this one as one polar group, and I call this one as one polar group. So what is the meaning of polar group? Means that set of conductors will have one pole formation, one pole. The other will have one pole. So here, how many poles will be having? 2 poles, right? So let us see. Now the question is, by how many ways we can place the conductors? Means we can place the conductors by 2 ways. One is concentrated, the other one is distributed. Concentrated winding, the other one is distributed winding. See, the detailed discussion of this concentrated and distributed you can learn in your synchronous machine. But as the stator construction of a synchronous and induction both are more or less same. So that is the reason I'm trying to give the outlines, what are called as concentrated, what are called as distributed. So distributed windings. So with this, your stator construction will be over. Once again, I'm reminding you for tomorrow's schedule. So tomorrow for the new batch, which was started on July 5th. So there is no class for them. Induction machine class is not for them. No, it is not there for them. But for the previous batches, the old batches, the batches which was started previously, for them, whatever the pending topics you are having in FNS, so will be taken tomorrow. And for us, for all batches, right? So the next class for induction will be on Sunday, 5 to 9. See, I'll speak to the manager today and I'll see if the class is preponed at 4. But that will be from Monday if he agrees and if the management agrees. So we'll see that, right? Don't worry. One of the student called me, sir, even if you take little advance, we don't have any issue. So I'll speak to them. If it is possible, I'll arrange the class. Is it okay? Confirm me. Right, done. So it is with your consent, right? With your consent that we'll discuss on Sunday, not today. Fine. So distributed winding. So what is the meaning of concentrated winding means? See, I'm trying to draw this part, this part. So you can see in this part, how many conductors you are placing? Only one conductor. You can see only one conductor. I'm trying to take this part, right? So how many conductors? One conductor if I'm having only one turn. But now if I'm having more than one turn, I need to go for 3 conductors. So what is the meaning of concentrated means? I'll try to draw a cut view like this. Cut view, only cut view I'm drawing the. So here, if I'm numbering this one as 1, 2, 3, 4, 5, 6, then here 1, 2, 3, 1, 2, 3. If the conductors are placed one over the other, if the conductors are placed one over the other, such arrangement we call it as concentrated. It is something like looping. The conductors are placed one over the other. On the other side, 180 degrees, the remaining conductors 4, 5, 6 are placed one over the other. So that we call it as concentrated winding. So what is the meaning of concentrated? The conductors are placed one over the other. So these are called as concentrated winding. Concentrated winding. Is this point clear? Is this point clear? Concentrated means the conductors are placed one over the other. So what is the advantage? What is the disadvantage we have with this concentrated winding means? See, I'm trying to draw roughly the easiest way of placing those conductors. This is one slot. This is one slot. Instead of showing like a cylinder, I'm showing like a simple representation. So the angle between these two is how many degrees? 180 degrees. You know that. So here this is one conductor, one conductor, one conductor, one conductor, one conductor, one conductor. 1, 2, 3, 4, 5, 6.
then you know that the polarities of current in conductor A 1 and conductor 4 are different. See, when I was explaining you the concept of phases, I told you that if you want to decide the voltage across a turn, we need to decide the voltage across a conductor. If the voltage across a conductor is say 5 volts, then the voltage across a turn will be 10 volts. Like that, if I'm having a coil, then in that coil, if I'm having 3 turns, then what will be the voltage? It is 30 volts. I hope this is clear. So here, if I want to get the total voltage, I need to know the voltage because of the first coil. What is that? 1 and 4, 2 and 5, 3 and 6. 3 and 6. So let me consider due to 1 and 4, the voltage is something like 10 volts. And due to 2 and 5, the voltage is 10 volts. And due to 3 and 6, the voltage is 10 volts. Then if I'm going to add up all these voltages, what is the voltage I'll get? 30 volts. So it is a voltage 30 volts. 30 volts. So what will be the voltage across that? It is 30 volts. Is this point clear? Confirm me. Confirm me. So the voltage per turn is 10, like that. 3 turns means 30 volts. But fortunately or unfortunately, knowingly or unknowingly, if you look into the wave shape, waveform of this voltage is not a pure sine, it is a square voltage. It is a square voltage. So that means if the voltage is a square voltage, indirectly it leads to a harmonic. What is that harmonic? We'll see. So we are having harmonic in that, right? But what is the good thing we are having with this is, good thing is, as the area covered is more, then you can see it is a DC value. And you know that in case of a DC value, the RMS value, average value, peak values are same. So what is the RMS value for this output voltage? Means it is same 30 volts. So RMS will be the same 30 volts. So this is the nature of your output voltage waveform. Once again, what is the meaning of concentrated winding means? I can tell like this. If I am having a coil, generally we have a coil like that only. If I am having a coil with more than 1 ton, in that case, we'll be having more than one conductor under one polar group. In that case, I need to place those conductors in a particular slot. If all those conductors are placing one over the other, one upon the other, we call such conductor or such winding as a concentrated winding. Concentrated winding. What is the good thing with this concentrated winding is the RMS value will be good. The RMS value is, say in this case, 30 volts. The maximum will be there. So this is called as concentrated. The disadvantage is the nature of output voltage waveform waveform is not sinusoidal. Sinusoidal. It is a non-sinusoidal waveform. Is it clear? Is it clear? Confirm me, all of you. Right. What is the other possibility that we can place these conductors? Means instead of placing one upon the other, we'll try to place the conductors one side the other. That means we are going to distribute the conductors between the slots, right? So what are called as distributed winding. See, I'm just trying to give the outlines. So in case of your synchronous machine, your teacher will try to work out numericals on this, but I'm trying to explain the differences here. Please understand. So distributed windings. Distributed winding. What is the meaning of distributed winding? Means those conductors are not placed in the same slots, one over the other, but those conductors are distributed between the slots. It is like this. If I'm trying to draw like this, so those sides should be equal. Please try to understand. So those conductors are distributed here. So they are not placed one over the other, but those conductors are distributed. So this we call it as a distributed winding. Now let me draw the voltage waveform. This is one set, and after 180 degrees, we'll be having the other set. So this is 1, this is 2, this is 3, this is 4, this is 5, this is 6. Then what is the voltage we are having between 1 and 4? It is like this, 10 volts. What is the voltage because of 2 and 5? It is after a slot angle, not along the same axis. So you can see it is along this axis. This is a slot angle gamma. Similarly, like this, 10 volts, 10 volts. So if I'm finding out the resultant of all this, right? So if I'm trying to find out the resultant, you can see, so here 10 volts rise. After that here another 10 volts rise, again 10 volts rise. 10 volts falls, 10 volts falls, 10 volts falls. So you can see the output voltage waveform is merely sine wave. If I'm increasing the number of turns, you can see merely sine wave. So this we call it as which windings, Baba? Distributed windings. So can I say, instead of placing the conductors one over the other, if the conductors are placed one next to the other, we call it as a distributed winding. Is this point clear? Confirm me. Is this point clear? Confirm me. Right. Then what is the drawback we are having with this means? You can see here we have full area we have. That is the reason the RMS value is more, but you can see some of the area is chopped here. Some of the area is chopped here. As a result, what happened to the RMS value decreases, the VRMS value will decrease. But what is the nature of that output voltage waveform? Merely sinusoidal. It means that harmonic content. See, if any voltage or any MMF waveform is purely sinusoidal, then I can say no harmonic. If other than sinusoidal, there are unwanted voltages or unwanted harmonics. So we can say what is harmonic, we'll see, right? So it is, you can see when compared to this one, this voltage, it is merely sine. Compared to that, harmonic content in this are less. Is it clear? Confirm. So I can say the advantage is nature of output voltage waveform is merely sinusoidal, and hence harmonic content is reduced. Harmonics are reduced. Harmonics are reduced. I hope this is clear. Now the question comes, how much voltage is reduced? So here the voltage is more, but here the voltage is less. How much is reduced? So that is decided by the distribution factor, right? So what is the distribution factor given for nth harmonic means KDN is equal to sine m n gamma by 2 by m sine n gamma by 2. So here m represent slots per pole per phase, gamma represent slot angle, it is 180 by slots per pole, and here n represent order of harmony. Don't worry, I'll tell order of harmony. So what is the definition for this distribution factor? Means it is the EMF with distributed winding by EMF with concentrated winding. For example, you have calculated this for a fundamental, first one. So it is 0.95, say 0.95, say. So what is the meaning of 0.95 means when compared to your concentrated winding,
the EMF with the distributed winding is only 95%. So how much reduction in the voltage means 5% voltage is reduced. If the distribution factor is say 0.5, so how much voltage is reduced? 50% magnitude is reduced compared to your concentrated winding. So this is something about your distributed winding. So can I finally conclude like this? If I'm having a coil with more than one turn, then in that case, so we need to place more than one conductor in one slot. So how to place those more than one conductor means they can be placed in the single slot with conductors one upon the other. We are naming it as a concentrated winding, and otherwise we can place those conductors one side the other in the different slots, and we are calling it as a distributed winding. The advantage with the concentrated winding is the ERMS or the magnitude of the RMS value will be more, but the nature of that output voltage will be non-sinusoidal. But if I'm trying to distribute those conductor, the output voltage waveform will be merely sine, and hence harmonic content will be reduced. But what is the drawback we have means a part of the voltage magnitude is reduced, and that reduction in output voltage can be measured with the help of a distribution factor. Is this point clear? Confirm. Is this point clear? Right. So this is something about concentrated winding, distributed winding. Next one is full pitch and short pitch. See, once again, I'm reminding you, these are the concepts related to your synchronous machine. But as we are discussing about the stator construction, I'm just taking whatever is required for induction. That's all. Nothing more than that. Right? Full pitch and short pitch. Short pitch. So what is the meaning of full pitch and short pitch means? See, I told you that when we are considering a turn, what has to be the angle between the conductors? 180 degrees. Why? Because you know very well, in order to add up the voltages, we need to connect the conductors which are lying on opposite poles. Then only the voltages will add up. Then only the angle between those two conductors will be 180 degrees electrical for full pitch. Is it clear? Confirming? Confirming? Right. Now, what is the meaning of full pitch? See, I'll consider two conductors which are under these poles. This is here. This is here. Here. So what is the angle between these two now? 180 degrees electrical. 180 degrees electrical. It is full pitch. Full pitch. But what is the main problem we are having with this means, as the distance between those two conductors is far away, this inactive copper requirement will be very, very high. So this is inactive copper requirement will be more. Inactive copper will be more. Why? Because the distance between two conductors is too large. Is it clear? Is it clear? So for full pitch, only few what happens to other ray? Please raise the hands. Right. So for full pitch, what is the angle between those two conductor sides? Means 180 degrees. But what is the main problem we are having with this? Means the inactive copper requirement will be more. So for that, what I'll try to do means, I'll try to pull the other conductors little bit closer, but it is still under the south pole only. It is corded. It is short pitch by some angle alpha. It is pulled from the south pole. Then what happened to this inactive copper requirement now? You can see the inactive copper requirement is reduced. Copper is reduced. When inactive copper requirement is reduced, what happened to the cost? Decreases. What happened to the weight? Decreases. So this we call it as a short pitch. So for short pitch coil, the angle between those two will not be exactly 180. It will be less than that alpha, where alpha is your cording angle or short pitch angle. So the angle between the two conductor size is 180. Then obviously the inactive copper requirement will be more,
and voltage is also maximum. If it is 5 volts, then it is also 5 volts. Why? Because those two conductors are exactly under the maximum flux area. Why? Because I told you that if any conductor, so this is a north pole. So this is a north pole. So this is a south pole. Let me assume. So coil means how many conductors will be there? Two conductors. So one conductor is here. Assume that maximum voltage 180 degrees. Another conductor will be there. Maximum voltage. Then the voltage in both the conductors will be maximum. Already I told you. That means if any conductor is coming and exactly under a pole, the voltage will be maximum. But very unfortunately, when this conductor is here, if this conductor is say here, so that is not exactly the south pole, it is little bit away from that. So what is the voltage here? It is not maximum, it is less than maximum. So here you can see in this, the conductor voltage may be 5 volts, but the conductor voltage is less than 5 volts. So in case of short pitch, the total voltage in a loop, in a turn will be reduced. Is it clear? Is it clear? Right. Once again, I'm repeating. What is that full pitch coils means? If the angle between the two conductor sides is 180 degrees, then it is called as a full pitch coil. If it is a full pitch coil, as the angle between north and south is 180 degrees, then if one conductor is under north pole, as it is a full pitch, the other conductor will be under the south pole. The voltage induced in both the conductors will be maximum. But if it is a short pitch, the angle is not 180, it will be slightly away from that. Then the voltage in that conductors will be less than maximum, and hence the total voltage in that loop will be reduced. That we call it as a short pitch. So the advantage is we are able to reduce the inactive copper requirement, but the drawback is a part of the voltage is reduced in short pitch. Why? If it is a full pitch, then you can see exactly these two conductors will be under the poles. Voltage are maximum. If it is a short pitch, then this conductor is not 180, it is less than 180. So it is something little bit away. Then that voltage in that conductor will be less and the loop voltage will be less. Is it clear? Is it clear? So whatever the voltage that is reduced with a short pitch is represented or it is accounted with a pitch factor. Pitch factor. It is given by cos n alpha by 2. For example, for fundamental, if it is 0.95, say the value is 0.95, then I can say when compared to a full pitch winding, in case of short pitch, the voltage is only 95%. That means because of dragging of that conductor, 5% of voltage is reduced. But the good is the inactive copper requirement is reduced. So finally, so my voice is audible or any strucking? No strucking. Right, it is audible. Right. So I think there is no struck. I'm writing all the statements, okay? Don't worry. I'll write, don't worry, I'll write. Fine. Okay, don't start from 4, sir. Okay, it is not like I'll inform to them. It is, I have no power in that. So whatever they told, 5 is okay. So we'll see 5 only. Fine. So finally, I'll write a statement. What is the statement I'm writing? See, Baba, till now, every point I'm writing on the board. Don't worry. First I'll explain, after that I'll write. So the stator windings, the stator windings are distributed and short pitch to reduce the harmonics and to save the inactive copper. But the disadvantage of
Disadvantage of distributed winding and concentrated winding is that the EMF magnitude is reduced and it is accounted with distribution factor and pitch factors given by the above, right? So this is something about your distributed winding, full pitch winding, concentrated winding, and short pitch windings. Is it clear? All of you confirm. All right. So this completes your stator construction. See, once again, I'm reminding you, all the discussion what we had are required, and it is very important for you in the coming days are being an electrical engineer, right? So every point I'll be taking in the coming days. So this is one stator construction. Next one is rotor construction. Rotor construction. As the name says, a rotor means a rotating here, a rotating part. So here, basing on this rotor construction, we have two types of induction motor. So the classification of induction motor is done basing on the rotor construction. First one is squirrel cage, or in simple cage rotor, right? Why the name? We'll see. The other one is slip ring or wound rotor. Some people call it as wound rotor. So wound means in Hindi ghav, right? Some ghav, but it is not a ghav. Wound means the coils are being wound on the rotor construction. Wound rotor or wound rotor, right? Please remember that. Then whatever the state are, so people are raising their hands. So once. Please, all of you lower the hands once. Right. So just I'm moving the screen. It is moving. Right. So my voice, audio, and everything are clear. Now raise the hands. Right. Done. That is clear. So whatever the stator we have discussed till now, if I am using with a squirrel cage, then what is the name I can give to that machine? Means it is a squirrel gauge induction motor, or in simple a cage motor, right? Similarly, whatever the stator we have discussed till now, if I'm using with this, then what is the name I can give it? Means it is a slip ring induction motor, or in simple wound rotor induction motor. So this is the classification of induction motors, right? So can I say based on the rotor construction, we have
Why Papa, people are raising the hands? So from my side, I don't have any issue. You can see the screen is moving. Voice is audible. So just text me if you can hear me everything. Dimyasri, repeated and short pitch windings. No, sir. No, no. I didn't get you. See, one thing, I'm just giving you the numbers. If anyone, if any issues here, you can ask me. If you're not able to get your turn now, so you can call me. No problem. Right. Oh, time ho gaya. Anonymous attendee. Oh, already 8:30. Oh, okay. Anyhow, I'll stop. No problem. So anyhow, I'll not this doubts is must for me, right? So I'll stop for today. So once again, I'm repeating you. So tomorrow, my class is not there, and for new batch, there is no class for tomorrow. Day after tomorrow, we have our as usual schedule 5 to 9. But for tomorrow, the previous old batches will be having the remaining topics in I don't know, fault sensibility, FNS, right? You can just attend that class. Tomorrow you have the same class from 5 to 9. That is power system, right? So I'll come back, just wait. I'll bring that earphones, I'll come back. Right, right. So first of all, let me see the question and answers. Huh. Right, we'll see anything is there. Everything is clear, sir. Oh, time up, sir. Fifth line, 1, 2, 3. The stator windings are distributed and short pitch to reduce the harmonics and to save the inactive copper. But the disadvantage of distributed winding and concentrated winding is that the EMF magnitude is reduced and it is accounted as distribution factor, right, ma? See, I can take up to 9, but tomorrow, next class onwards. Yeah. See, one question from anonymous attendee. Sir, for all types of motor, the relative speed between the two fields is 0 or not. It is a must. Say, we have seen with respect to a DC motor, but in case of induction motor, I have not shown the relative speed between the two fields is 0. When I'm talking about the working principle, after this construction is over, then you can see there how the relative speed between the two fields will be 0. That I'll take care. Don't worry. That I'll be explaining there. It is a must. Sir, do we use lap winding or wave winding? So if you look into this, in case of your DC machine, we'll be having the concept of lap and wave winding. Here we have distributed and concentrated winding. Please remember that. Timing 5 to 9. See, whatever the number I have given, that is the only WhatsApp number. Please remember. Sir, K is equal to 0.95. Why you consider? See, just I have taken one example of KD is equal to 0.95. I mean to say that if you calculate with the given data. If you calculate, if the value is turned to be 0.95, then E mean to say that when compared to your distributed winding, so concentrated winding, the voltage with the distributed winding is only 95% for that. So does flux line cuts and pass? No, it is the meaning of cutting. So it is something like you take a waterfall, then if you try to move the hand in that waterfall, it looks like your hand is cutting the waterfall like that. Mistake in pink color, fifth line. Okay, what is that? The same doubt. The stator windings are distributed and short pitch to reduce the harmonics and to save the inactive cover. But the disadvantage of distributed, yeah, please, I understood. It is not distributed and concentrated, distributed and full pitch, sorry, short pitch. Short pitch. Windings is that. Thank you, Baba. Thank you. Voltage waveform. Already I told you how to draw. See, Bhavani, sir, in induction motor we have to apply Fleming's left hand rule, but we have applied Fleming's right hand rule. See, it is not the question of motor or generator, motor or right hand rule or left hand rule. See, if you want to find out the direction of induced EMF, it is the right hand rule. And if you want to know the direction of mechanical force, it is the left hand rule. So if you remember, so in case of your this explanation, to know the direction of induced EMF, I have used right hand rule. So please don't confuse. EMF right hand, force left hand. So we have not used that right hand rule to know the force. That in the working principle I'll explain. Salman Khan, sir, how come the square wave? See, I told you that the voltage per turn is 10 volts. So from if I take north to south, so it is 10 volts, again 10 volts, again 10 volts. It is something like 30 volts. But if they are shifted by some angle, so you can see it is a stepped wave. In that case, it will be nearly a sine wave, right? Salman. Right. In concentrated winding, EMF is not, but you wrote EMF reduce. I have corrected that, Bhaskar, please. So as we move away from the magnetic field, the changes will be less, not like the changes will be maximum. See, explain the pole formation in single phase. See, very simple, Baba. In single phase, so we have two conductors which are carrying the currents in opposite direction. So if you apply the right hand thumb rule, in each case you can see. So this is a single phase. One conductor is carrying current into, the other conductor is carrying outwards, right? Then you can see if I apply the right hand thumb rule, the directions of flux lines is like this, then this is a north pole and this is a south pole, right? Timings. Not required. Timings. 4 pole means it is the poles per phase. It is only A1 to A4, that's all. Okay. Right. So anyhow, everything is fine. I'll go for the calls. Now I'm attending the calls. Yeah,
Hello,
Pawan,
sir.
Pawan Kumar.
Sir, good evening, sir.
Good evening, Pawan Kumar.
Sir, four-pole formation చేశారు కదా సార్?
4 pole design.
Yes, sir.
It is
అక్కడ
4 pole per.
A1
this
A2
one.
అడ్జసెంట్ ఎందుకు తీసుకున్నాం సార్? అంటే మనం ఆపోజిట్ గా తీసుకోవచ్చు కదా స్టాటర్
See, A1, A2. See, A1, A2 is one coil. Okay. A3, A4 is one coil.
సార్.
Okay. These two coils are connected in series.
సార్
What has to be the angle between those two coils? 180 degrees electrical.
ఓకే ఓకే సార్.
So as it is a 4-pole, then you can see the electrical angle will be like this. So that's the reason I have taken 90 degrees mechanical. You know the relation, right?
ఓకే ఓకే సార్.
Right. Pawan, still?
ఓకే సార్.
Okay.
4 సార్.
Okay. Thank you, Baba. Yeah, Imtiaz Pasha.
Good evening, sir.
Good evening, Baba.
Sir, in designing the four-pole per phase machine, is there no, sir?
Yeah, you can see on the board.
Means it's direct connection to A1 to A2, no, sir?
It is end connection, sir. A1 and A2 are joined.
Sir, in machine we gave the A1 to A2 or A1 to
See, this internal diagram you will not find it externally. Only you find out these two terminals.
yes, sir. Means I'm asking which we will use, sir, first one or second one?
Pardon? I'm not getting you. Say this is phase. Say this is neutral. So these are something like overall it is A. This is A dash. So that is your phase A.
सर मेरा मतलब क्या है? मतलब
क्या बाबा बोलो?
आप जो बोले ना फर्स्ट वन में A1 से A2 one and second one is the A1 A2 same direction में, तो number of poles will be decreases by P by 2.
No. See, it is not like that, Imtiaz Pasha. See here, this is one coil, right?
Yes, sir.
So this is one coil, right?
Yes,
so
sir.
what are the conductors of coil 1? It is A1 and A2, right?
Yes, sir.
Right, these two are joined with end connection. So this is forming one coil, right?
Yes.
Similarly, what are the conductors of second coil? A3 and A4, right?
Yes.
These two are joined like this, right? Then if I place the same conductors here, A1, A2, A3, A4, and if I try to go for a positive cycle, you can see these are the instants of currents, right?
Yes, sir.
Then how many poles we have now?
4 poles.
So how many pole machine it is?
4 pole machine.
Up to here, any doubt?
No, sir.
Now for the same placing of conductors A1, A2 like this, instead of joining these conductors with A1 and A2 internally, if I join A1 with A3 internally, not externally, A1 with A3 and A2 with A4, and if I give the same supply, then in the same stator core, how many poles will be formed?
2.
2. That means if these 4 terminals A1, A2, A3, A4, if they are available outside the stator, then if I join these two and if I join these two, how many poles will be formed?
4 poles.
If I break this, if I join like this, how many poles will be formed?
2 poles.
That means we can change the P pole machine into P by 2 pole machine by changing end connections, right?
Yes, sir.
Now you are clear?
I'm clear. In
yeah.
first, sir.
Yeah, Imtiaz, I'm there. Yeah, please ask your doubt.
तो दोनों में by default कौन सा रहता, first one या second one?
It is not the question of by default, Baba. See, I'm having an induction motor. Okay. I want to control the speed. Right?
Okay.
If I want to control the speed, if I'm giving it to 4 pole, Ns is equal to 120 F by P. If it is 4 pole, the speed will be approximately 500 RPM. When you change the end connection, the poles will become 2. Then the speed will be approximately 3000 RPM. It is not which one. So initially, if it is like this, then the speed will be nearly 1500 RPM. If you change it to like this, then the speed will be nearly 3000 RPM. Understood? So if you want to control the speed, you have to change. But generally, I'm talking about unless and until you want to control the speed by pole changing, we don't bring the terminals out. Generally, no terminals are brought out.
Only if you want to control the speed, in that case, the terminals are being brought out. Imtiaz, is it clear now?
Yes, sir. Sir, one more.
Now you are clear with this?
Yes, sir. One more is there.
Please.
Sir, in full pitch and short pitch, which one will you use, sir? Short pitch or full pitch?
Already I told you, we use only short pitch. Why? Because we need to reduce the inactive copper.
But voltage will reduce, no, sir.
It is only uncountable. Only some 2-3% it will be.
Okay, sir.
And one more thing is, some unwanted harmonic voltages can also be reduced with short pitching. So what is that your teacher will explain in your synchronous machine. So we prefer to go only with short pitch and also with distributed winding. Is it clear?
Yes, sir.
Right.
Thank you, sir.
Right, Imtiaz. Right. Hemalata.
Sir, good evening, sir.
Good evening, ma.
Sir, you have shown the formation of 4 poles, no, sir.
Ha, ma. Just now I spoke to one of your friend. Yeah, please,
Yes,
ma.
sir.
Please.
Sir, the current direction towards above diagram, sir.
This one.
Here, A4 current direction is same, sir.
So see, it is reverse, huh?
Yes, sir.
Yeah, please, ma. It is printing mistake. Sorry. Thank you, Hemalata. Very good. So it is a printing mistake. It is not explanation. Okay.
Yes, sir. Yes, sir.
Thank you, ma. But I have shown correct here, right?
Yes, sir. Yes, sir.
Right, ma. Thank you, ma. Thank you.
Nothing.
Right. Right. Next. Next. Amit Vikrant. Vikram.
Sir.
Good evening, Amit Vikram.
Sir, in that portion where you had asked the question that where the flux will be maximum of a pair 1 to 7 or 4 to 10.
Yeah, I'm going there.
Sir, actually, I had a doubt in that, like this terminology, what you are using, that the flux cutting and flux passing. What is
Yeah.
the difference between flux cutting and flux passing?
See, Baba, I'm assuming these are the two conductors of coil, right?
Yes, sir.
Now, in this, all flux lines are passing, right?
Yes, sir.
So let me assume that between these two conductors, 5 flux lines are passing. Okay.
Yes, sir.
The flux linkages are maximum or minimum? Maximum.
Yes, sir. Maximum lines are passing, sir.
It is maximum, correct?
Yes, sir.
Now, when I'm trying to move this coil like this, then you can see this coil is coming perpendicular. So is there any flux lines passing to this coil now? All the
No,
lines
sir.
are like, no, right? So initially, how many flux lines were there?
5.
Now, if I move the coil like this, how many flux lines are coming?
Sir, 0.
That means changes are maximum or minimum? Were 5, but now 0. How many changes are there? 5 changes are there.
Yes, sir.
So changes are maximum or minimum?
Maximum, sir.
EMF will be?
Maximum.
That's what. Understood?
Yes, sir. Thank you, sir.
Right, Baba, right.
Sir, one more, sir.
Baba, please.
Sir, here you have given that for every pole like from 2, 3 and onwards, you have given different just below the graph you have given. Na?
Yeah. Why?
So, sir,
Because see, these conductors are under which pole? North pole, above conductors.
Yes, sir, North Pole.
Then you apply the same right hand rule for the below conductors, you get the opposite polarities. So if I take this one as positive values, then what about the cross? Negative.
Negative, sir.
That's the reason I have taken negative. Is it clear?
Yes, sir.
Right. Vikram, समझा रहे?
Thank you, sir.
Right, Baba. Shiva Gopi. Shiva Gopi. Shiva Gopi. Not there. Yeah.
Hello, sir. Good evening.
Good evening, Baba.
Sir, yesterday class, sir, I have one doubt. Please go through the discussion of open source.
See, Baba, Gopi, so yesterday doubt means you call me on number. I'll explain you. Let us continue 2 days. Gopi, you have my number, Gopi?
Yes, sir. But my actual doubt is not for the about discussion. It's a general question, sir. That's why I
Yeah,
asked.
you ask what is the general question. I'll tell. No problem.
Yes, sir. In open slots, maybe in semi slots, whatever it may be.
See, your voice is something, and behind you there are some disturbance. Now you please tell.
Sir, what is the practical air gap length between rotor and stator? That's what my general question is.
Say it is minimum should be 0.2 mm,
Yes, sir.
right? Minimum. Then
Minimum.
basing on your size, the diameter will be added. So finally, I'll give an equation, approximate equation I'll give to calculate the minimum air gap length. Minimum should be 0.2 mm.
Depends on the
Size.
power capability. It will vary, sir.
Yes. If it is a larger machine, it will vary. It is not like fixed.
Okay. Okay, sir.
Right, Baba, right.
For another question, sir.
Baba.
Sir, in semi slots, in bottom there will be an edges. We prefer for induction machines. You told that semi slots will be preferred.
It is not like edges. So the semi-closed slots are having the partial advantages of open and partial advantages of close. That means 50% of that, 50% of that. That is the reason we are preferring. It is not like.
My question is that inside the bottom edges, it is like a compact design of in view of a mechanical point of view.
See,
even though we prefer semi slots other than open slots.
No. See, that is also the access to the farmer coils is also possible here, but it is not like only with respect to one point. We prefer to go with semi-close, right? So with respect to many comparisons, we prefer to go with semi-close.
Okay, more points are dominated advantages. So that's why you prefer semi slots, sir?
Correct.
Okay, sir. One more question, sir. Sir, in open slots, that's what in heat delivering. Sir, in detail you discussed how heat will produce in open slots.
Slots will be open, right? So in that we will be placing the conductors.
Okay.
So you can see when that rotor is rotating, so air is also rotating. As the slots are completely open, the air which is there in the area will be hitting that conductor.
Yes, sir.
Definitely what happened to the temperature of that conductor?
Okay, you as per your discussion, conductor heat will reduces, but my question is that whatever it may be the heat, that will be entire frame will be closed path, na? That's how heat will be delivered to the outside surface. That's what my question.
See,
how can we say that which heat will be reduces out for outside the surface?
See, every machine will be having a cooling fan.
Okay.
At the same time, every machine will be having your so-called as heat sinks.
Okay, what do you mean by heat sinks?
Already I told you yesterday.
Yes, sir. Yes. In graphical, that's I am.
Every machine will be having a heat sink. So all these are responsible for reducing the heat.
Okay.
What I mean to say in large machine means if you are using a closed slot or a semi-closed slot, the cooling will not be that much effective compared to your open slots.
Okay.
So that is the reason it is better to go with open slots compared to other slots. I hope you are clear with my analysis.
Yes, sir. I clear, but for same measurements will be taken for a high HP motors which were used in industries purpose.
I didn't get your question.
And that's my reducing the heat. We use heat sinks as well as fans or any other chemical materials.
Everything we use only open slots. So see, when you are using semi-closed slot, so for cooling purpose you need to go for more fans and other things. But if you are using an open slots, so whatever the air that is there in the air gap will be providing a better cooling. That means the heat rise will not be that much.
Okay.
Is it okay, Shiva?
Okay, sir. Thank you, sir. And that's what my question, sir. General
you are clear with my question? No? Answer no?
Yes, sir. Okay.
Right, Shiva. Right,
Okay.
Right.
Okay. Thank you.
Right. 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 Bhavani. Bhavani.
Good evening, sir.
Hama, good evening.
Sir, in induction motor rotor, you have drawn the rotor circuit,
Mhm.
and in upper conductors, you have put a dot symbol. Sir, why it is leaving the conductors on upside?
See, Amma, that's what I applied here. Which rule I have applied here? Fleming's right hand rule. That's what
Right.
That's what I told you, na. I had a long discussion. The field is rotating clockwise. Assume that the conductor is moving counterclockwise direction.
Yes,
So
yes,
field
yes.
is downwards. So conductor is like this. The current is outwards. That is what I have shown, Bhavani.
Okay, sir. Then it should be north and south, na, sir. You have drawn it south and north.
Ekkadamma. So I have taken initially. So you can
South side leave అవుతుంది కదా sir అక్కడ.
see it is now whatever the picture you are seeing on the board. You are talking with respect to that picture.
Yes, sir.
Yeah. So it is not like question of leaving and entering, Amma. It is based on two things. One is in which direction this field is rotating. So in which direction the stator field is rotating?
Clockwise.
So with respect to this clockwise, so these conductors will be having outward current. Why? Because you can see
Okay.
here. Amma. So
Okay.
with respect to this pole, these will be having the cross.
Okay.
So it is with respect to the direction of the field. This is what. Now as the circuit is closed, this EMF will circulate a current. Okay.
Okay. Okay.
Now you apply right hand thumb rule for this. If you apply, then a south pole is formed here, a north pole is formed here. Is it clear, ma?
Yes, sir.
So these rotor poles are due to that induced currents. Understood, ma?
Okay, sir. Okay, sir. And one more thing, sir. అర్థమైంది సార్.
ఇది అర్థమైందమ్మా?
అర్థమైంది సార్. Sir,
Right.
one more thing, sir. In full pitch and short pitch, you have told that in short pitch, some EMF will be induced, will be less అన్నారు కదా sir.
అవునమ్మా,
Sir,
correct.
as the poles are rotating through all the stator thing, then it doesn't matter where the what do you say, where the conductors are placed.
See,
He's
amma,
covering all the conductor now, sir.
no. See, whenever we talk about short pitch, it is with respect to a single coil, single turn first. Like that, we are having n turns, all are connected in series. So when we are talking about a single turn, so if
Okay.
angle between the conductors is 180 degrees, then what is the voltage in a single turn? Say 10 volts.
Yes. Yes,
అర్థమైందమ్మా?
sir. Yes, sir.
If the angle between this is not 180, it is less than 180 degrees. The voltage will not be 10 volts. It is less than 10 volts.
Okay. Okay.
Understood?
Okay.
Why? Because if it is less than, one conductor will be under north pole, the other conductor will not be exact under south pole. It will be little bit away from south pole. When it
I
is
thought it is with respect to north and south pole.
లేదురా. Now you are clear,
Ah,
amma?
okay. Yes. Yes,
Right.
sir.
Right, amma.
That answer. Thank you,
Right.
sir.
Right, Nana. Right. Ramakrishna.
Yeah, good evening, sir.
Good
So-
evening, Ram.
So in that rotor, you have said that 4th and 10th conductor have maximum flux changes. So when they are perpendicular, 5 to 0.
See, I am not getting your question. Now you please tell me with respect to which one?
No, sir. In that rotor,
Yeah,
total
this-
12 conductors. Yes, here, sir.
Yeah, please tell.
So 4th and 10th conductor, when they become perpendicular, there will be maximum flux changes that are 5 flux lines to 0 flux lines.
Yeah, assume that. That means the changes in that particular coil
4 and
Yes,
10
sir.
will have maximum, the EMF will be maximum.
But sir, similarly, 1 and 7 conductors, they have 0 flux lines, and then when they become perpendicular, they will have 5 flux lines. So here also flux changes, no sir, maximum 5.
See, Baba, that's what I'm talking with respect to this instant of time. When this instant of time, which coil will be having maximum voltage, I told. So the coil 4 and 10 will have maximum voltage. When those poles are rotating, then after 90 degrees, that coil 1 and 7 will be having maximum voltage. Understood?
Yes, sir. Yes, sir. Okay.
Right, right. Done. Is it clear?
Yes, sir. Clear. And similarly, you have taken conductor carrying current as cross now into the Y is that.
Which one? This one, huh?
No, in first in design of two-pole machine starting you have taken.
This one.
You have said that conductor carrying current is taking so into the cross mark.
If not, you take outwards. If you are taking this one outwards, you take this one as inwards. If that is the case, this will be north pole, this will be the south pole. That will be oscillating.
It is assumption or you have taken?
It is an assumption only.
Okay.
Okay. Why? Because there are two possibilities. Maybe this
Yes,
or
sir.
maybe that. Understood?
Okay.
I'm
Yes.
assuming that. I'm assuming that. See, I'm having a machine like this. Before ice, there is a machine like this. In the machine, there is a coil, and I'm supplying the current from this side. When I'm supplying the current from this side, so upper conductor is taking the current or bringing the current back.
Taking.
Taking means with respect to my eyes, it is moving away or it is moving towards me.
So moving away.
Cross or dot?
Yes, sir. Cross. Okay.
If the same one is the bottom conductor is collecting the current, it is coming towards my eyes. Dot or cross?
Dot, sir. Dot. Okay.
You are clear, Ramkrishna?
Yes, sir. Yes, sir. Okay.
Right.
Okay. Thank you.
Okay.
Okay. Thank you, sir.
Sai Charan Reddy.
Hello, sir.
Yeah, Baba.
Sir, in rotor, you took 12 conductors and you explained us that one.
Yeah. 1 second. Yeah, please. This one. I took one example. Yeah, bol Baba.
Sir, in this, can you please tell that how this E is equals to BLV is satisfied, sir? And,
See, here it is not.
Relate, sir.
See, very good. So here also E is equal to BLV only. But the thing is, here L is fixed, but which one is moving?
L is fixed. Yes, sir. Flux is changing, sir.
Flux is moving.
Yes, sir.
That means, according to Faraday's law, whenever a conductor is moved under a magnetic field, the conductor cuts the magnetic flux lines, correct?
So can we say that there would be a relative motion between conductor and flux, but no, but not especially conductor or flux. If there is a relative motion, then we can say that it cuts.
This is what I have explained. This you can see.
Yes,
Here,
sir, yes.
the moving conductors are cutting the flux lines. Here,
yes, sir.
Moving flux lines are cutting the conductor. So whenever
Yes,
there exists a relative speed, either of this can happen. Is it clear, Charan?
Yes, sir. Yes, sir.
Right, Baba. Right.
Sir, in another point you told that EMF induced means we cannot say that flux is maximum, but the rate of change of flux would be maximum, no, sir.
What I mean to, I told that, see, if any conductor is coming exactly under a north pole, yes, I told you that if it is coming exactly under a north pole, the voltage will be maximum, right?
Yes, sir.
Any pole, the voltage will be maximum. But we cannot say whether that voltage is positive or negative. Why? Because it all depends upon your direction of the field. That is what I told. See, I'll take this north pole. So there is one conductor here. So the voltage will be maximum in this, correct? If the voltage under this will be maximum or minimum? If a conductor is exactly coming under a north pole, again not any field, the voltage in that conductor will be maximum or minimum?
We will see the initial flux, sir, for that. Initial
see, I told you
zero.
that. See, I told you that the poles are rotating, and I am considering one instant of time. Here, the conductor is exactly coming under north pole. So, what will be the voltage? Maximum or minimum?
Yes, sir, maximum.
The voltage will be maximum. It is
so
a dot
here,
or dot or cross, I can't say. If this pole
yes,
is
sir.
moving like this, it is dot. If the pole is moving like this, it is cross. That is what I told.
Okay, sir. Okay. So we will assume that this conductor initial flux is 0, and when the
Not
when the
initial, the
north pole
initial, when the initial, see this conductor is initially here, right? And it is moved like this, the flux cuttings are maximum, the changes are maximum, EMF is maximum. If that field and conductor are remaining stationary for a long time, there is no EMF at all. Why? Because there is no flux cutting, there is no change.
Yes, sir.
Understood? This is only
Yes,
when the field is moving.
Okay, sir. Okay.
Now clear, Sharan?
Okay, sir. Okay.
Understood?
Sir,
అర్థమైందా?
అంటే మీరు ఫస్ట్ లో చెప్పారు కదా సార్, ఏదంటే ఇనిషియల్ ఫ్లక్స్ గురించి, ఫైనల్ ఫ్లక్స్ అంటే చేంజ్
ఇప్పుడు
అయిన ఫ్లక్స్ గురించి
వాట్
డెల్టా.
ఎవర్ ద క్వశ్చన్ యు ఆర్ హ్యావింగ్ విత్ రెస్పెక్ట్ టు విచ్ ఫిగర్ యు ఆర్ హ్యావింగ్ డౌట్, యు టెల్, ఐ విల్ ఎక్స్ప్లెయిన్.
దిస్ ఫిగర్
It
ఓన్లీ
is
సార్.
not this figure you ask. Now you tell. Now my question is, the poles are rotating, right? I am
Yes, sir.
considering at an instant of time now. I told you all this. The poles are rotating. I am considering at an instant of time now. If that is the case, in which coil the EMF will be maximum? I told. The question was like that. For example, assume this pole is initially here. Then you can see in 4 and 10 the flux lines are maximum. As this pole is already reaching here, then the changes in that coil 4 and 10 will be maximum, and EMF in that coil is maximum. This is what I told.
Okay, sir. Okay, sir. Then my doubt is like relative doubt, sir. Relative, like 1 and 7, you told that EMF is minimum like 0, sir.
0. Why? Because the changes are not there. Why? Because all the flux lines are passing through that.
Okay, sir. So even when we take that poles are moving also, the north pole was initially at 1, sir. So the 1 is maximum at before time. After reaching n to now wait, assume to position like that is 4, sir.
4.
So n is moved from 1 to 4, sir. One conductor to fourth conductor.
Yes.
So the first conductor, one conductor also have a change, sir. Delta flux.
How can you say change, Baba? See, this is conductor 1, this is conductor 7, right? So this
Yes,
is
sir.
conductor 1, this is conductor 7. Now all the flux lines are traveling now.
Yes, sir.
Now this is conductor 4, this is conductor 10. Now is there any flux lines passing through these conductors now between 4 and 10?
No.
So that means when
yes, sir.
Yes, sir. So when compared to your conductor 1 and 7, so there are 4 flux lines passing through this. If the voltage in these conductors 1 and 7 is 0, so here there are no flux lines passing, then the voltage in this conductor 4 and 10 is maximum.
Yes, sir.
ఇక్కడ ఎన్ని ఫ్లక్స్ లైన్స్ వెళ్తున్నాయి? 1 కి 10 కి మధ్య, 1 కి 7 కి మధ్య ఎన్ని వెళ్తున్నాయి?
4, sir.
4 వెళ్తున్నాయి. అంటే మాక్సిమం ఫ్లక్స్ లైన్స్ ఎన్ని? 4 అనుకుందాం.
4, sir. Yes, sir.
ఇప్పుడు ఈ 4 కి 10 కి మధ్య ఎన్ని ఫ్లక్స్ లైన్స్ వెళ్తున్నాయి?
4 కి no, sir. No fluxes.
అంటే దీంట్లో 4 వెళ్తున్నాయి, దీంట్లో వెళ్ళట్లేదు.
దీంట్లో no flux. Yes, sir.
అంటే ఎన్ని వెళ్ళాల్సింది? ఎన్ని వెళ్ళాలి? యాక్చువల్ గా 4 వెళ్ళాలి. ఇప్పుడు ఎన్ని వెళ్తున్నాయి?
అంటే జీరో.
వెళ్ళట్లేదు. అంటే ఏంటి? అక్కడ వోల్టేజ్ 0 అనుకుంటే దీని వోల్టేజ్ ఎంత ఉండాలి?
మాక్సిమం.
అంతే కదా? Why?
Yes,
because
sir.
the poles are moving. So now the pole position is like this. So initially the flux lines are 4, but when it is coming here, the flux lines are becoming 0. That means when compared to this 1 and 7, the voltage in 4 and 10 will be maximum. That is what I told.
Yes, sir. Okay, sir.
ఇప్పుడు అర్థమైందా నీకు?
Yes, sir. Sir,
నీ డౌట్ ఏంటి? నాకు అర్థం కాదు.
డౌట్ అంటే నేను ఫస్ట్ లో మీరు చెప్పిన దానికి దీనికి రిలేట్ చేసినప్పుడు నాకు కన్ఫ్యూజన్ వచ్చింది సార్. మీరు ఎక్స్ప్లెయిన్ చేసినప్పుడు చాలా క్లారిటీ ఉండే సార్. ఆఫ్టర్ అంటే ఫస్ట్ లో చెప్పిన దానికి రిలేట్ చేస్తే అప్పుడు కన్ఫ్యూజన్ వచ్చింది సార్.
ఇప్పుడు ఏం లేదమ్మా, అక్కడ ఏంటంటే నీకు కండక్టర్ మూవింగ్.
ఎస్ సార్.
హలో,
అక్కడ ఫస్ట్ లో కండక్టర్ మూవింగ్.
ఇప్పుడు ఏంటి మూవింగ్?
ఇప్పుడు ఫ్లక్స్ మూవింగ్ సార్. ఫీల్డ్
మూవింగ్.
ఎస్ సార్.
అర్థమైందమ్మా ఇప్పుడు?
అర్థమైంది
రైట్ నాన్న, రైట్ రైట్.
సార్. మనము కండక్టర్లో డీసీ
Right.
ఫ్లక్స్, కండక్టర్లో డీసీ ఈఎంఎఫ్ ప్రొడ్యూస్ అవుతుందని చెప్పొచ్చా సార్ మనం ఎప్పుడు?
లేదు, ఏసీ
అంటే ఇక్కడ మీరు 10 వోల్ట్స్ ఇక్కడ
ప్రొడ్యూస్ అవుద్ది. ఇప్పుడు ఈ కండక్టర్స్ లో ఎలా ఉంది నీకు?
అంటే
ఎక్కడ ఏదో చూపిస్తే చెప్తాను నేను.
అంటే ఇక్కడ సార్
ఇదినా
ఇది పిక్చర్స్ లో తీసుకున్నారు కదా సార్, డిస్ట్రిబ్యూషన్ అండ్ కాన్సన్ట్రేటెడ్ పిక్చర్స్,
ఇదా
వైండింగ్స్
ఇదా
ఇక్కడ సార్, ఇక్కడ 10 వోల్ట్స్
ఇదేనా?
ఇది సార్, ఇదే సార్.
సో మళ్ళీ ఇది మళ్ళీ నెక్స్ట్ ఇది వెళ్దా, ఇది నెక్స్ట్ మళ్ళీ సౌత్ నార్త్ కి వెళ్దా? ఇది వెళ్ళొద్దుగా.
అంటే ఒకటే ఇన్స్టెంట్ లో తీసుకున్నారు సార్. ఓకే సార్,
అర్థమైందమ్మా.
ఎస్ సార్, ఎస్ సార్.
మళ్ళీ వెళ్ళొద్దు కదా నాన్న అది.
ఎస్ సార్, ఎస్ సార్, కరెక్ట్.
ఓకే,
ఎస్ సార్.
రైట్, డన్.
డన్ సార్.
రైట్ రైట్, ఓకే. రవి కుమార్ గద్దెం.
సార్ గుడ్ ఈవినింగ్ సార్.
ప్లీజ్ మా గుడ్ ఈవినింగ్. రవి కుమార్ గంధం.
Sir, due to network issue, I had missed something, sir. Can you explain?
See, your
Sir,
network issue, my network issue.
My network issue.
Okay, please. Ravi Kumar Gandham.
Yes, sir. Sir, the directions of north and south poles, I didn't get in some points.
Where? Which one?
We have discussed that basic. We have discussed sign form. Yes, sir.
Where?
Down.
This one?
No, sir.
This one?
Next.
This one?
After this one. Sir,
This one?
here. Yeah. Yes, sir. Next before.
Yeah.
Sir, here.
See here, which one is moving?
Sir.
Which one is moving here? Field or conductor?
Conductor is moving, sir.
In the second case, conductor is stationary. You can see here, stationary conductor.
Yes, sir. Yes. Second case, it is.
Which one is moving?
Field is moving, sir.
So if you want to apply Fleming's right hand rule, in this case, you have to assume that the conductor is moving in opposite direction.
Okay, sir.
Then you apply the same thing, right? So if the field is moving down,
yes,
if
sir.
the conductor is assumed to moving in counterclockwise direction,
okay.
then in which direction the EMF will be outwards?
Outwards.
Understood, Baba?
Yes, sir. Sir, behind.
Yeah.
Sir, this one.
Here the conductor is moving.
Yes, we have to take the magnetic field downwards direction. Is it right, sir?
Yeah, understood.
Actually, I am little bit confused to apply the right hand Fleming's here.
Now you take this board and you apply that, you'll get. You take the paper, you'll get, no issue. Understood?
Okay, sir. Yeah, another doubt, sir.
Right.
Sir, in somewhere north and south poles are there, sir. Next concept.
This one?
Yes, sir.
Yeah, please ask.
Directions.
Which one?
North and south directions in rotor.
In
rotor.
See.
Yes.
So these are the currents which are induced, right?
Yes.
Dots, correct?
Yes, sir.
By applying which rule? Fleming's right hand rule.
Yes.
Then if the circuit is closed, there will be currents. So if I apply the thumb rule, so what will be the direction of flux lines? You can see it is like this, right? It is like this, right?
Yes, sir.
Is it clear?
Yes,
so
sir.
This is air, and you are going into core. Air into core is which pole?
Sir, actually,
so this is air.
Actually, I'm little bit confused at where the air is taken, and we have assumed in.
See, it is not like it is not the question of confusion. You see, it is a core, rotor
Yes,
core. So
yes,
this
sir.
is the stator core. So what is the area between the cores? Air gap.
Okay. Yes, sir. in before
So
that.
this is what So you do one thing, you read today, you'll get it. Otherwise, you call me on my number. Is it clear?
Yes, sir.
Kumar.
Yes, sir. Okay.
Hello.
Okay, sir.
Right. Samjha Baba. Right.
Yeah, yes.
As a Shiva.
So good evening, sir.
Good evening, Baba.
Sir, I have a doubt in design of two pole machines.
Shiva, your voice is not that much clear, Shiva.
Sir, can you hear me, sir?
Now I can hear you. Please.
Yes, sir. I have a doubt in design of two pole machines. Can
Yeah.
you just scroll a bit up, sir?
Yeah, this one.
Yes, sir, here.
Already I explained, na? So the same question was asked.
No, sir. Here we are having, I mean, like single phase and with a coil with one turn only, sir. Hence, we are getting two poles, right, sir? So if we like the same conditions are applied for three phase winding, then how we are getting the same two poles again, sir?
See, you are giving excitation to all three phases at a time or only single phase at a time?
No, sir. All the three phases are doing.
This is what I happened.
Yes, sir. So is sir, let me explain. Just correct me if I'm wrong, sir.
Yeah. So this is what I explained for all three.
Yes, sir. Here, suppose in the first diagram, here the I mean like the flux between the A and C dash will get. I mean the middle they'll be cancelling each other, and between C and B, the flux lines will get cancelled, and hence we are getting a one single north pole, right, sir?
Correct.
So here, this north and south pole is for per phase or for whole, sir?
See, it is not the question of per phase. I told early. We design poles per phase. When you are giving excitation, so those two poles will be oscillating. But when you are giving excitation to all three phases, those two poles will be rotating. At a time, you can find only two poles, as you are designing only two poles per phase. But the nature will be dependent on your given excitation.
So, okay, sir. Okay, sir.
Understood now?
Yes, sir. Yes, sir.
Right. Clear, Shiva?
Yes, sir.
Right.
Yes, that's it. Thank you, sir.
Right. Right. No one is raising the hands. It's half day.